Hey, we're gonna have the picture day later on. So I see some of you already brought the nice shirts. So very nice. Uh, so you will see the nice shirts in person today when people stand up and walk around, and in the picture as well. We probably may ask them to sit in the front, stand in the front for the picture. So okay, so today I'll give you some applications of eigenvalue interlacing. So I'll try to. So I have this. It's not something formal. It's more like a feeling or a belief. Or okay, so I'll just say my belief is that any combinatorial parameter um, may be related um, to some spectral parameter. So I'll try to give you some examples for some various combinatorial parameters, and we'll see the connections between them. There are some connections that people have found, but maybe there are other more that maybe you can find. So I'll go through some combinatorial parameters and I show you how they relate to eigenvalues. So the first one, let's start with edge connectivity. So as before, we have a graph gamma, and we assume gamma is connected. And now the edge connectivity is denoted by kappa prime of gamma is the minimum of the number of minimum cardinality of a set of edges f, where f is a subset of my edge set, such that gamma minus f is no longer connected, is disconnected. And one can see there is some work that one has to do, and this is going to be essentially the size of the minimum size of a cut. Okay, so this is the minimum this is in terms of subsets of vertices S of let me give it more space of the cardinality of the number of edges between S and its complement, where S is a subset of vertices. So what I'm writing here is that this number of edges between S and V minus S. This is a set of edges. Let me put it like a set, capital E. And the edge connectivity is the minimum number of edges that you have to delete such that you break the graph into some parts. Okay, so let me write it here so that you have it. So E of S, V minus S consists of all edges. So edges, I won't write them as sets. I'll just write them as words, X, Y, an edge, X is in S, and Y is not in S. Okay. Now, there is a general, so there's, Professor Karan showed you yesterday, there's work from Fiedler in 1970s related to this notion of algebraic connectivity, the second largest eigenvalue of the Laplacian. And Fiedler proved that, so if the eigenvalues of the Laplacian of gamma are, let's say, 0, which is mu1, less than or equal than mu2, less than or equal to mu(n), then what you have is that the vertex connectivity is greater or equal than mu2. So vertex connectivity, I denote it by kappa. I'll give you the definition in a second. Vertex connectivity is a little bit different. You want to delete, let me call this set T. So you want to find a subset of vertices T such that when you delete, you have some part X. So the rest of the vertices split into a part X and a part Y, such that there are no edges between X and Y. You separate X from Y. Okay, you disconnect the graph. Basically, you delete here, this part disappears, and then there's no edges. I mean, here it doesn't have to be connected, but there is some way of splitting the vertices like that. So this is vertex, and this vertex connectivity, so K of gamma is the minimum cardinality of T, where T is a subset of vertices such that gamma minus T is disconnected. Okay, you have to be a bit careful how you define them for complete graphs, but that's about it. Okay, for connected graphs, for the other ones should be the same. So this is a inequality from yesterday. This is the algebraic connectivity that this is a name that Fiedler used for it. It's an important parameter. We'll see later in other similar contexts. But there is an exercise in graph theory that it's always like this: that the edge connectivity. This is the edge connectivity. So the edge connectivity is always greater or equal than vertex connectivity is greater or equal than mu2. So this inequality you saw yesterday, and this one you should try to prove or figure out a proof for it. Okay. So this is one way of relating, one general way of relating for general graphs the edge connectivity. But in some situations, so for example, for regular graphs, one can do much better and one can obtain results that are, in some sense, best possible. So let me tell you some results about edge connectivity for regular graphs. So this is something that I did in 2010. There is a paper in linear algebra and application 2010, eigenvalues and edge connectivity, something like that, in regular graphs. So there'll be, I won't present you the whole paper. I'll give you some ideas, some results, but the details are in the paper in case you're interested. Okay. So the first result from here is a little bit, okay, so I have, let gamma be a deregular graph. With, so I'll have it connected, deregular and connected graph with eigenvalues d, which is the largest one, strictly bigger than lambda 2, greater or equal to lambda n. Okay, so then there's a bunch of, so there's the general inequality is something like this. So d gamma will have n vertices. So I'll put it somewhere. Gamma is VE and cardinality of V is n. So if you have something above the lambda 2, did I write it? Yeah. If the spectral gap d minus lambda 2 is greater or equal than some number, it will seem a little bit complicated. K minus 1 times n, you'll see in a second where it comes from, n minus d minus 1, then k prime of gamma is greater or equal than this number k. Okay. So I use for this number k, and this one is backslash kappa. Okay. Now, 1 prime, in the case that if n is greater equal to 2d plus 2, and now I have something better. D, let's put it this way. I'll put it in terms of lambda 2 now. Lambda 2 is less than or equal than a little bit more than d minus 2. D minus 2 plus 4d plus 1 if d is even, and d minus 2 plus 6 over d plus 1 if d is odd, then the edge connectivity of the graph is maximum equals the degree. So which one? What is it? What? K here would be like a parameter. K would be something, you can think of it as something between 2 and maybe um, uh, D. So it'll be like the edge connectivity that we're targeting, okay? So the general result here, if you have this inequality, this spectral gap bigger than this, then the edge connectivity is at least K. I'll show in a second how this comes about. And then if I'm shooting for k equals d, which is the maximum that I can, and n is bigger than 2dd plus 1, then this is the bound that you have, a little bit more than d minus 2. Okay, so if you see the comparison here, this inequality is great. It's a general inequality, and it applies to all graphs, regular or not. And you saw yesterday that this inequality k greater than mu2, you can characterize the equality case. You can have like some joins or something that people have done that. Now, if you try to just apply this inequality over there, so that's one thing you have to be careful. Like sometimes when you go for a particular case of a problem, you have to take advantage of that particular case structure. So the fact that it's irregular, it's quite strong. So you should take advantage of it. So here, this mu2 in general is d minus lambda 2. So this inequality, you see k gamma minus mu2, for if gamma is d regular, this mu2 will be d minus lambda 2. So the lower bound that you'll get here, it will always be less, you'll be less than d minus lambda 2. So this inequality by itself, for regular graphs, won't be sufficient to just give you that the vertex connectivity is maximum. Okay, you need to do something else. And also, if I just apply this like here, what does it tell me? Well, edge connectivity is at least the d minus lambda 2. Okay, that's fine. But it turns out for regular graphs, you can do much better if d minus lambda 2 is a little bit more than d minus lambda 2, a little bit, it's 2 minus a little bit. So then the edge connectivity is maximum. Okay, so yeah. Okay, so let me give you so here when I was doing this result, I had again another belief. It's good to have some beliefs, even if sometimes maybe true or not. So I wanted, for regular graphs, I wanted to prove like something called best possible results. So let me show you something called 2. And okay, I'll give you the simpler result first, and then it's not the right order, but anyway, let's do this. If I proved if lambda 2 is strictly less than d minus 3 plus square root of d squared plus here it's d plus 3 squared minus 16 over 2, then k prime of gamma is greater or equal to 3. So this is this is part A. So you have this weird bound here, guarantees edge connectivity at least 3. And what's so special about this is that this bound is best possible, meaning that there are d regular graphs. I think there is one with lambda 2 equal to this d minus 3 plus square root of d plus 3 squared minus 16 over 2, and k prime equal to 2. So you cannot drop this, you cannot make this bound any smaller, because you will be in trouble. So that's what I mean about results that are best possible. That's what I was trying to do. I was trying to find the best bound here that you can put here that guarantees that you are 3 edge connected. And we have something else here, which is a bit for edge connectivity too. And here it works for d odd. So I'll show in a second why we don't have to consider D even for this problem. If rho of D is the largest root, the largest yeah, root of some cubic polynomial x cubed minus d minus 3x squared minus 3d minus 2x minus 2, and lambda 2 is less than rho of d, then k prime of gamma is greater or equal to 2. So again, you have here some kind of bound similar to this one. This is a solution of a quadratic. This is a solution of some cubic. So if lambda 2 is less than some number that depends only on d, then your edge connectivity is at least something, and b, it's the same thing. There are d regular graphs with lambda 2 equals rho of d and k prime equals 1. Okay, so that's kind of the idea. Okay, so now I kind of bored you or scared you with a bunch of these kind of weird results at the beginning. So let me give you a list, the idea about where do you get something like this, for example, and then I'll give you an idea about how you get better results and so on. So for all these results, for like 1 and for 2 and 2a and 3a, the idea is to prove the contrapositive. So I don't know if you guys all know the contrapositive. Okay. So for example, here for this result, the contrapositive would be if k prime of gamma is strictly less than k, then d minus lambda 2 is strictly less than blah, 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 this thing that I have here, k minus n, d plus 1. So generally speaking, that's how like any of these results can be proved. I mean, that's the first step. Okay, so there are more details. Yeah. Do you guys have questions? No. Okay. So the proof sketch. Okay, so what do we do here? We have from here k prime kappa prime of gamma less than k. What does it mean? It means there is a partition. So it means essentially that kappa prime of gamma is less than or equal than k minus 1. And which means that there is some partition into S and V minus S, where here you see, so I'll denote by E of S and V minus S the number of edges between the S, so the cardinality of this set. This is less than or equal than k minus 1. Okay? And now it kind of, okay, how do I get the eigenvalues involved into the thing that you have to keep in mind? There too, like it's either quotient interlacing, something about induced subgraphs, or is this business with quotient matrices and partitions? And here, for edge connectivity, the partition kind of, it's staring you in the eyes. So say, okay, let's do it. So then the quotient matrix is the following. B. Okay, so do I have a letter here? Okay, I'll just keep this. So what's the quotient matrix here? The easiest ones, the easiest values to get here are the values in the entries 1, 2 and 2, 1, because those involve the number of edges in between the parts. And that number of edges, you have some name for it, E. So here, what should be the value of B in the position? So this would be my V1, this would be my V2. What would be the number of, what would be the entry in the B1, 2? the number of edges between V1 and V2 divided by cardinality of V2. So it's the number of edges between S and V minus S divided by the cardinality of S. Okay? And then here, it's almost the same thing, number of edges between S and V minus S divided by N minus cardinality of S. And as before, because the graph is K regular, here you will have K minus this. D. Thank you. And here you'll have D minus N minus cardinality of S. So you see, again, this is the thing that I told you before, that when you want to apply this, you have some kind of combinatorial property structure in mind, edge connectivity in this case. It somehow forces some kind of partition on you, and then you get the quotient matrix, and by this Hemmer's interlacing, you will have some kind of relation, okay? Sometimes it will be good, sometimes maybe, not so good, but you have to check to see what you get. So now for this matrix B, lambda 1 of B, like I said before, and you may want to check this, but for all regular graphs, when you do quotient matrices, the row sums will equal the degree all the time. So lambda 1, you won't get anything there. I mean, you'll get something useful. Lambda 1 of B is D. This is useful because it allows me to calculate lambda 2 of B fairly quickly, because now I have the trace. So lambda 2 of B is the trace of B minus D. And now the trace of B, you have a D from here, you have a D from here, and you subtract a D. So it'll be D minus something. It looks a little bit weird, but it's not so bad. Okay. And you can simplify this a little bit, D minus. If you bring these two things to the same, to a common denominator, it will be cardinality of S times N minus cardinality of S. You'll have the number of edges between S, V minus S, and then these two things add up, and they add up to N. So that's what you get. Okay. And now, so you get something like this here, and just from Hemmer's interlacing, you will get that so you will get something that lambda 2 of my B graph is greater or equal than lambda 2 of B, which is this value. And that's essentially how you get the first result, because the other thing is, what do you know about number of edges between S and V minus S? Is at most K minus 1. So this thing will be greater or equal than D minus N times K minus 1, because here this one is less than or equal than K minus 1, but it has a minus in front. So it works in your favor. Cardinality of S, cardinality of N minus S. And now to take care of this and to compare it there, I have D plus 1. And you can just argue that cardinality of S has to be at least D plus 1. There's some small argument that you can do to show that. Okay. So this is very easy. Now, so this is a general result, and I don't think it's tight, but it works for any K. And then if you apply this with these conditions, you replace K by D, and you do some calculations. I'm not going to go through all algebra. You get something of this form here. Okay, so this is just from, but I won't do it here. Let me tell you a little bit about these two results. So in this case, like I said, I found the best bound. Let me show you what happens there. How does that work? Okay. Okay. So I'm going to erase. I will erase here just to make space. Okay. So for both of these problems, what happened is somehow I had in mind, like I tried various graphs, and I thought that I guessed, conjectured what would be the graph that would be best possible. So again, I proved for both 2a and 2b, you prove the contrapositive. So for 2a, if you want to prove 2a, you want to prove something that if this edge connectivity is less than or equal to 2, then lambda 2 is less than or equal than this. And here what happens is essentially what you're trying to do. We're trying to figure out among all edges whose edge connectivity is almost 2, which one has the largest second eigenvalue. Okay? And so this was the graph that I come up with. You have a graph here. It has to be deregular. Okay? So let me see how this works. So you lose one here. Here you put a k d minus 1, and you make a join. So let me pick some d. So let's say d equals, okay, let's say d equals 4. So here I will have 3 vertices, complete graph. Okay, and on this side you have the same thing. So this would be kd minus 1, 2 vertices that are, there's no edges here, no edges here, two parallel edges here, and so on, the same thing on the other side. Now, this graph is deregular because every vertex from this vertex has one edge here and it has all the d minus 1 here, the same for all these 3. A vertex here, because it's in the kd minus 1, is going to have d minus 2 degree in here, but it has 2 more edges, so it's deregular. And then, surprise, surprise, so this is, where are we with exercises? 23. 23 with question mark or 23 with exclamation mark? It's, yeah, yeah. Yes, yes. Yes, yes, yes. Yeah, so the smallest, yeah. Exclamation. Yeah. Exclamation? Yeah. Yeah. So just to, okay, if P implies Q, it's the same thing as not Q implies not P. So, if, yeah, thank you. If lambda 2 less than something than this, K prime less than 3, which is less than or equal to 2, implies lambda 2 greater or equal. Thank you. So, this is a graph, I guess, that will have the smallest lambda 2. It's kind of, if you play around with it a little bit, is probably the smallest, in terms of order, the smallest deregular graph that has edge connectivity too. Because deregular, you have to have 2 edges, and you kind of see how much can you have on each side. And you can have kind of deep, here you have d plus 1, d plus 1. So now, exercise 23. Calculate the eigenvalues of this. Now, I already gave you a hint because I drew this blob, bomb, 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 meaning that this partition looks like it's equitable partition. So this partition is equitable, and in general, so let me call this matrix X, because that's, I think, X tilde D. That's how we call it in the paper. So this will be for D. So if I start from here, what's the degree inside? D minus 2. What's the degree next is 2, and then 0, 0. So this is a case where you have an equitable partition in more than just 2 parts. It's 4 parts, okay? Here, going back, I see d minus 1. Inside, I see 0, but going to the right, I see 1, and I have 0. Here, I see 0 in the first part, 1, 0, and I see d minus 1 to the other side. And at the end, I see 0, 0, 2, d minus 2. Okay? So now I'll give you the answer to make it easier for you. I think, did we calculate this? Yeah. So Lambda 1 of this matrix, D. So you just have to calculate the other. So the other two, so essentially the characteristic polynomial uh, will be x minus d, x plus 1. And from the look of this, you know you'll get this and you'll get the conjugate of it. So you'll get a quadratic, which is x squared plus 3 minus dx plus 4 minus 3d. So from the quotient matrix, you get 4 eigenvalues. So you have 4 eigenvalues. The graph size is what? The graph is 2d plus 2. So I have to have 2d minus 2 other eigenvalues. And you do that's why the exercise is not just to calculate this computation, because this is Sage Math or other computer program can do it for you. But you should do this other thing about the computing the remaining, the eigenvalues corresponding to eigenvectors which are perpendicular to the parts. You see here again we have this kind of join, and this will correspond to those all one matrices in the all those all one block matrices in the adjacency matrix, which you can by the theorem that we proved in the we stated in the equitable partition part, you can make them disappear. So here you have these 4 eigenvalues, and the remaining ones will be minus 1 to the power with multiplicity 2d minus 2. So from the quotient matrix, you get 4 eigenvalues, and then these are going to be the eigenvalues that correspond to eigenvectors that are constant on each of the parts. And then okay, what about the rest? Well, those eigenvectors, they have to be perpendicular on each of the parts. And what you have here, you have a complete graph on d minus 2. So d minus 1. So at the end, you have 4, and I think this should be it. So exercise 23. Okay. Don't worry, there's exercise 24 coming next, which is harder. So let me tell you a quick thing about this one, because this one is weird. You have this cubic, and where does this come from? And you have, first of all, you have this thing about d odd. Okay, so you only have to consider, again here, for this one, you look at the contrapositive. And what is it? If k prime of gamma is 1, because the graph is connected, so it has to be 1, then lambda 2 of gamma has to be greater or equal than this rho of d. Now, again, the same thing here. Where this rho of d came from, and what d is odd? Why did I only look at d is odd? Well, you don't consider d even, because when d is even, the edge connectivity can never be 1. The edge connectivity is at least 2. Why is that? Well, if you have, let's say, a subset S, let's say I have here, I'll call it E for now, number of edges. If I sum up the degrees in S, I do sum of x in S of degree of x. There are 2 ways to sum it up. One, the graph is D regular, and I have S cardinality of S, so this is D cardinality of S. That's the easy way. But also, you can look at it when you have a vertex here. We did this before. You have some edges that go inside, and you have some edges that go outside. So if you split the edges according to the ones that go inside and the edges that go outside, what do you count? You're going to count these edges between S and V minus S exactly once. And inside here, it will be like a handshaking lemma. You will count each edge twice. So this will be 2 times the number of edges inside S plus the number of edges between S and V minus S. This is always, and this is kind of the basis why for regular graphs all the time these row sums in the quotient matrices, whatever quotient matrices you take, it will be D. So now, if D is even, D times S is even, this is even, So the number of edges between S and B minus S will always be even. So I don't need to worry about edge connectivity 1 for even degrees because it will never happen. That's the basic thing. Okay. So now I'll finish the part about edge connectivity telling you where does this row of D come from. And see where the picture is. Okay, so so it's a you have here you start here with a K2. The next blob will be what I call MD minus 1 bar. This is the complement of a perfect matching in KD minus 1. This is also called a cocktail party graph. So D, remember D is odd. So D minus 1 is even. D minus 1 is even. So this is the same thing as a D minus 3 regular graph on D minus 1 vertices. You know, if you have D minus 1, D minus 2 regular on D minus 1 vertices, it's a complete graph. If you have D minus 3, it means you have taken a perfect matching out of it. That's all it is. So let me do the picture here for D equals 5. You can do it for D equals 3 if you want, but that's even easier. So a complement, how did we do it here? A complement will be something like, it's actually C4 in the case of D equals, because the diagonals of it are the ones that we take out. Then you have a vertex here adjacent to everything here. Then you have here you will be like the edge connectivity is 1. You do the same picture on the other side. And now you have to see how you connect these other things. So here will be also a join. And here will also be a join. Okay. And now, again, I gave you the 1 part, 2 part, 3rd part, 4th part, 5th part, 6th part. Of course, you can say, why don't I could put these two together. I can put these two together. I can put these two together. But that gives me like information about 3 eigenvalues. But if I do the partition into these 6 parts, I will get information about 6 eigenvalues. It's a, so this one, let me change. This one is Y, I think in the paper, and this one is X. So this partition that I put 1 blob, 2, 3, 4, 5, 6, this is equitable. And you can do this 6 by 6 is better than n by n, okay? So then you're going to have a lot of zeros, and what do you have? You have a 1 here because of the edge here. What is next? A 4, but in general, for general D minus 1. D minus 1, 0, 0, 0, 0. And this kind of partition will also tell me that the graph is D regular. Now here, when I look back, I see 2. When I look inside, I see D minus 3. When I look to the right, I see 1. Okay. Here, it's 0. D minus 1, 0, 1, 0, 0. Here, 1, 0. D minus 1, 0. And then fifth one, 0, 0, 0, 1, D minus 3, and 2, 4, and then 1 and D minus 1. Okay. It looks like big, I don't advise you to do it by hand, but, if you have nothing to do, do it. So Let me see, did I calculate? Yes. So the characteristic polynomial here would be x minus d, x minus 1, x plus 2, and then times, there's a cubic, and the cubic is the one that I mentioned there, x cubed minus d minus 3 x squared plus minus 3d minus 2x, I think minus 2, something like that. Did I get it right? Yeah. So it's yeah. Now, so this graph has how much? You have 2, you have d minus 1. So with another one, you have again 2d plus 4. 2d plus 4. You got 6 from here, and you can argue that, okay, 6, d, 1, minus 2, and 3 cubics. 3, they will be real and distinct. And then the same thing, what are the rest? So these are 6 eigenvalues from here. And exercise 24, find the rest. There should be how many? 2d minus 2. And they're going to be minus 2 with multiplicity d minus 3, 0 minus 1 with multiplicity 2, and 0 with multiplicity d minus 1, something like that. And so you need to have the whole spectrum to argue that this is the second largest eigenvalue. The largest root of here is the second eigenvalue. And the largest root from here, so I didn't mention, but this row of D is between, is in the interval d minus 2 d plus 4, d minus 2 d plus 5. So that's pretty much where it is. It's not a rational number. And this number here is roughly how much? Is in the interval d minus 4 d plus 2, d minus 4 d plus 3. Also something like that. Okay. Okay. So again, yeah, it's now okay. I didn't tell you how you prove these results. So first of all, you guess what the target value is, which comes from these graphs. And again, kind of, how do you guess? Well, yeah, that's a good question. You try things. You play around with these graphs, and somehow it seems like all the time the graph that will work is the one that has the smallest number of vertices. So you try to pack these things as much as you can, and then you still have to prove. So in this case, so I showed you 2b. I showed you that there is a graph with this parameter. This is the graph, and you have to fill up the details. And I showed you, I guess you also have 3b. There is a graph. This is a graph, and this will have second eigenvalue rho d, and you can see that it has edge connectivity 1. But you still have to prove 2a or 3a. So how do you prove it? So again, you have to prove this. And so what you do, you're going to try to, you start with a general deregular graph, and let me erase here. Well, what do you know? The only information you know is that your graph looks like this. You have one edge here, and then you have two parts. Okay, and you can argue, because the graph is deregular, you have one edge here. This thing is going to have like d minus 1 edges here, and these graphs also have degree d. So here you can argue that you have to have something like at least d plus 2 or something like that. You have to argue that this is the case, some kind of lower bound. And then you kind of try to go towards the structure that you have from here. So you have the value of rho of d. You have the value of rho of d, which is here. So you have to argue, in each case, if my graph has this property, then the second eigenvalue is bigger than this. So how do you do that? Then in that case, you use this Hammer's interlacing. So for each case, you're going to do some equitable, some partition, which is not necessarily equitable. You'll do some partition into, you start doing partition into 3 parts and so on. And in each case, you prove that lambda 2 is a list of row of D. So you kind of, it's a proof by various cases, but that's the idea. So you use equitable partitions to get your candidate graph, and then you use Hamer's interlacing to get to the thing. Okay. All right. So I'll stop here about edge connectivity. Before I move on to the next parameter, any questions? So yes. So you want to make the edge connectivity as long as possible and then give some conditions. Yeah, you want to, like, for specific edge connectivity, you like to say, okay, what's the best bound that implies that edge connectivity? And here you can do it with 1 and 2. It gets much more complicated if you. I didn't do it for larger K because it gets more complicated. What's the part was that you wanted D? Eh? First part, there was one A and one in much like it. Oh yeah. When you get the that one is just from the first part. You don't do like, you do just partition into 2 parts and you play around with that expression. The one with K minus 1 n D plus 1 n minus, like something like that. There you wanted to is the edge connectivity. We started with D. Also that also all B. No, like in that case, I wanted a condition that, so the edge connectivity, the biggest edge connectivity that you can hope for a D regular graph is D. And I wanted, okay, what's the best bound I can get with, in that case, with the least amount of work. And the best bound was this, the initial one with which has both like you take K equals D and you have N and so on. And then I wanted to get rid of N, and you can simplify it. You can get rid of N, but that's just algebra. Like you don't do much. You don't do anything much more than partition into 2 parts to get that condition. The condition that, so essentially, for the 1 and 1 prime that I show you, when you want edge connectivity to be D, you just need the spectral gap to be at least 2 minus a little bit, and that's guaranteed. And so I was happy with that. It's connectivity at least K. So that's the general one, but the point about that one is that general one is not going to be sharp for K. So then I said, okay, I have this general bound, but for K equals 2 and for K equals 3, I can get better results. And I just wanted to see if it can be done, and I did it for 2 and 3. And possibly it could be done for other values. You could have probably graphs that look like this, like 4 parts, but it's more work, and I didn't do it. Yeah. Okay. All right. Now, so yesterday I told you about this Hoffman ratio bound. Let me show you something more general. So second, and this one will be, how to say it? It's something about subgraphs of regular graphs. And it will be very similar to what we did for Hoffman ratio bound. So here's the result. This is in Hamer's thesis. So if you go online, you can look for his PhD thesis. You can find it in online. And I think 78. And it has something of as follows. So you have gamma be a D regular graph with n vertices and usual eigenvalues. Let's say it's connected, so you have something like this. Okay. Now, assume that gamma prime is an induced subgraph of gamma with n1 vertices. Now, just because the big graph is regular doesn't mean that an induced graph is going to be regular. So gamma prime will have average degree d1. So you have the big graph gamma, and inside here you have a gamma prime, you have n1 vertices, and you have some edges inside here. The number of edges is going to be n1 times d1 over 2. That's the number of edges of gamma 1. Okay? Eh?
It's induced subgraph, right?
Yes.
Do you mean the other vertices are isolated or something?
No, that's a number. So induced means that gamma prime has n1 vertices.
Okay, I was thinking of.
No spanning. Induced. So remember, induced, you get it from the big graph by deleting some vertices. Spanning, you get it from the big graph by deleting some edges. So, okay. So again, here it's okay. I have a big graph. I have a big structure. Let me see. Can I say something of anything inside it? Like if I pick something inside it, is there like can there be like what's going on in that graph? Is it like completely crazy and everything, or is this something under control? It turns out that there is there are some restrictions that one has to obey. So the restriction will be the following. Let me write it here. Then lambda 2 of the big graph is going to be greater or equal than n d1 minus n1d n minus n1 greater or equal than lambda n. So there's some inequality which involves the number of vertices in the graph. So there's some restriction on this d1. I mean, it involves the n1, but there is something going on here that you cannot just pick any numbers n1 and d1 and say, okay, this is going to work. You have some kind of constraints between them. Now, here, we'll see in a second, if d1 is 0, this inequality from this part, it gives you the Hoffman ratio bound. And this is just the same idea in the Hoffman ratio bound, the same proof. We'll do it in 1 second, but it's just here, you don't have an independent set. You could have edges. That's all it is. So, for example, let's say I wanted something here that the average degree is 1. Like sometimes maybe you're looking for an induced matching. If you have an induced matching, that's regular and you have the degree equals 1. And then you put here 1 and you will get you put here 1, so you'll get some constraint on n1. So you can play these games about what, And then if you have information about n1, if you know what n1 is, then you will tell you about, okay, your average degree is not just anything you want. It has to be kind of constrained, okay? So this gives you the constraint, okay? So it looks weird, but how do you prove this result? And this is, again, like I said, it's the same. Okay, I have this subgraph, n1 vertices with something going on inside it, and obviously I will have the rest, which has n minus 1. And you play the same game that we did for Hoffman ratio bound, but now you play it for this partition, and you try to see. So this partition, the partition into the vertex set of gamma 1 and the vertex and the rest, v minus v gamma 1, is not necessarily equitable, but has a quotient matrix, Let's call it B again. And what is going to be? Now you get something, because of our notation, what do you get in the first entry here? Which number is it? D1. Because that's D1. And here, by the same type of argument that we did, you will get D minus D1. then what do you get here? So here you have to do some work because you have to figure out the number of edges in between. Um, so what is the number of edges in between? We did it when I show you the edge connectivity was, you sum up the degrees here, you sum up the degrees inside here. What you will get d times n1, okay? And now that number d times n1, what will equal? It will equal 2 times the number of edges inside here, which is d1 times n1, plus plus the number of edges in here. So the number of edges d here. So essentially, this number of edges is dn1 minus d11. So then you have this. Yes, you will have d minus d1 n1, and you have to divide by n minus n1, and then you have the remaining thing, d minus d1 n1 divided by n minus n1. And from here, you play the same game as before. Largest eigenvalue is d. The second largest eigenvalue will be the trace minus d. The largest so the second eigenvalue of b, you calculate it from this matrix, and you will be between lambda 2 and you will be between lambda n. And kind of you can guess what lambda 2 is going to be from how it looks like. This lambda 2 of b will be exactly this. So this is exercise 25. Finish the proof here. So calculate lambda 2. Okay. All right. Okay, subgraphs. Okay, so okay. Now let me tell you about vertex connectivity. So here there are two inequalities. So I defined before k of gamma as minimum cardinality. I don't know why I call it S. Let's say S subset of vertices gamma minus S disconnected. And now you have Fiedler k of gamma is so again I gave you for algebraic for Laplacian, but if gamma is d regular, you have k of gamma is greater or equal than d minus lambda 2. So you see, vertex connectivity is harder than edge connectivity, and here, no matter what you do, if you just like the previous result, I showed you that if I have d minus lambda 2, at least 2 minus a little bit, edge connectivity is maximum. Well, this result cannot give you edge connectivity is maximum because what vertex connectivity is maximum, because vertex connectivity is what? Maximum should be d. And what do you get here? You get d minus lambda 2. Lambda 2 in general, I mean, if the complete graph, if you have the complete graph, then lambda 2 is minus 1, but we're not interested in the complete graph. You have a complete bipartite graph, you'll have lambda 2 equals 0, and after that lambda 2 is going to be positive. So here you're never going to get d. So there's, as far as I know, there is no general just spectral bound that tells you that if this happens, then, so that would be interesting to find if you want an open problem to work on, to think about what condition can I put on my regular graph such that the vertex connectivity is maximal, is D? That would be a nice problem. Now, the second part, I had this here. Let's see if I wrote it somewhere. This inequality, you can have equality. So equality in Fiedler's bound was characterized was characterized. I think it was Kirkland. I may miss some author. Kirkland, Molitierno, Shader, and there may be some author I forgot, and I forgot the eh? Neumann. Okay, there you go. So the students know. Thank you. Do you know the year too? Well, you can just say something. No, 2002. Very good, very good. And so for regular graphs, you actually can get equality here in here. And how does a graph look like? So it's, again, this is a consequence of the more general result for general graphs, but you can have something like you can have something here with k vertices. Let's say I have here h. I'll tell you in a second what h is. And here you can have a complete graph on d minus k plus 1. And here you have a k d minus k plus 1. So you have a join, so that the vertices here will have degree d because it's d minus k inside here and they have everything connected here with k. And inside here also what you need to do is you need to have this graph h is regular and you have to have the right valency such that the graph is d-regular. So this may not work for all k's. This would be, see, yeah, I think k has to be at least half of the d, but that will be a graph which you have this join, and this will be a graph in which this is clearly the vertex connectivity will be k. You delete this, it splits into two, but then you have to do some work to calculate lambda 2 to show that is exactly d minus k, but it's not too hard. Like you have these two things here and you can use that. Okay, so again, this is that's possible. Now here there is another inequality which is due to Krivelevich and Sudakov. So this is in 2006, and this is it's a survey paper called pseudo-random graphs. I'll talk a little bit about it maybe today or tomorrow. And so here the result you need, it's not quite in terms of lambda 2, so you have these eigenvalues. And there's a notation that was introduced by Alon to talk about lambda, which is the maximum, absolute maximum between lambda 2 and lambda n. So lambda may not be the same as lambda 2. So let me give you an example. So for Peterson, the lambda 2 is 1 because you have 3, 1, minus 2. Okay? But this parameter lambda, it's the maximum in absolute value of all the eigenvalue except the largest one. And you see here the negative 1 is bigger in absolute. So you have lambda equals 2. Okay? But for some graphs, it can happen that they're equal, but definitely all the time you will have this. Okay? So I'll tell you something about this parameter and how it comes into play about like something called expander mixing lemma in a little bit. But their result is that if lambda 2, if lambda, no, it's, let me put, they put it like this. So this is one, they prove that k of gamma is greater or equal than d minus 36 lambda square over d. So obviously they didn't bother to improve the constants here, and they give some examples in which they show that this lambda square over d term here is tight. But if you want again a project, you can look through their paper and you can see this bound very likely can be improved. But you can never get, I think you can never get to something about that will give you d. It's always, you see, it's always d minus actually something quite big. So this is, yeah, so these are the bounds I know about vertex connectivity. Okay, so what else did we have on the thing? Edge connectivity, vertex connectivity. Let me tell you about another. Okay, so another place where you can where eigenvalues relate to the structure, it's related to existence of matchings. So I think Professor Canal mentioned yesterday what or earlier in the week what the matching is. So a matching in a graph gamma is a collection of edges M. So M is a subset of E, such that no two edges on M share an endpoint. Okay, and this is a matching, and sometimes you're lucky you can find a perfect matching. So perfect matching is a matching in which every vertex of the graph is contained in some edge of the matching. So a matching is perfect. A matching is called perfect if every vertex of gamma, so a matching, let's call it M, every vertex of gamma is contained in, or clearly it has to be contained in exactly one, but in some edge of M. Okay. So let's do some examples. Um, well, clearly, if you have a perfect matching, the number of vertices has to be even. Okay, but just because the number of vertices is even doesn't mean that you have a perfect matching. So this is the simplest example. 4 vertices, try to match them, and you know. But I can even make you. Let's try to make 3 regular graphs. So this is a 3 regular graph. The vertex on the top has 3. This ones have 3. Everybody has 3. And I claim that this one doesn't have a perfect match. There is a reason. I mean, there is a general theorem which I'll give it to you in a second. But for now, if you just want to do it by hand, for small graphs you can do it by hand, by case analysis. Let's assume that so I claim that this one has no perfect match. And here you can prove it by case analysis. Assume that it has a perfect matching. The vertex here has to be contained in some edge. So let's say it's in this one. That's the edge there. Then these edges here, they will be okay. I can find a perfect matching. Now, what happens on this side? Because this edge is used, I cannot use this edge. So I have to use one of these two. So I have to use this one. And then I'm left to this triangle, and then I'm pretty much done, because in the triangle, no matter how I try to find a perfect matching, there will be a vertex that stays. Okay, so that's the idea. But in general, there is a famous theorem of Tutt, which gives you a characterization. So it says the graph gamma has a perfect matching if and only if for any subset of vertices S, cardinality of S is greater or equal than O of odd, let's say odd of gamma minus S, where odd of gamma minus S is the number of odd components of gamma minus S. So let me tell you in a second what that means. So maybe some of you have seen this theorem, and maybe you have proved it. The one direction is easy, one direction is harder. But so an odd component is a component with an odd number of vertices. There's nothing bad about it. So sometimes you call someone odd, you think there's something bad about it. But this odd component, it just has an odd number of vertices. Okay, so let me show you where this condition comes from. Okay, so I'll show you this implication. If you have a perfect matching, then this happens. Okay, so if assume gamma has a perfect matching, and let's take S here. Okay, this is S. Has some number of vertices. You could have edges in there. I don't care. When you delete S, you can have some components. I don't know. Let's say you have the odd one, odd two, odd Q, and you have here the even one, let's say R. Okay? The Q, Q and R could be 0, but okay, you have this situation. You have, when you delete it, and you have no edges between the components. Okay? Now my graph has a perfect matching. So inside each component, there should be, the component means connected, so there should be some perfect, there are vertices. So if there's a vertex here, there should be an edge from the perfect matching that is there. If there should be an edge. But because this component is odd, there will always be a vertex that is left out from this perfect matching. There could be more, but there's definitely one. That's the thing about odd. You cannot pair it up. So there will be at least one, okay, vertex out. Now, this vertex has to be in one edge of the perfect matching. That edge of the perfect matching, it cannot connect to here because these are components. So where does it have to go? It has to go to S. And the same thing happened for every odd component. Now, because these edges are edges of a matching, they cannot go to the same vertex. They must go to different vertices because the edges in the matching don't share vertices. So if you have here Q odd components, from each of these vertices, from each odd component, you will have at least one vertex that doesn't have a match in here. You will have a match in here. So you're guaranteed to have at least how many vertices in S? At least Q. So cardinality of S is guaranteed to be at least Q. And that's the proof, this parity thing. The other part is harder, and you have to come up with this perfect match. And this condition is for any S, so that's it helps. Now, let me show you how this was used to give an eigenvalue condition about. Am I finished? Should I take a break? No, I have 15 minutes. 15. Yeah. I always confuse 9 and 9:30. So, this study was initiated by Brouwer and Hammers. They have a paper in LAA, I think maybe 2007 or 8, something about eigenvalues and perfect matchings. And later on, so we used their idea and we did a bit more work. So this is a paper I wrote with one of my advisors, David Gregory, and Hammers, and this is in JCTB in 2009. Matchings from irregular graphs from eigenvalues. And let me tell you the result. So what we proved is the following. Let gamma be a d-regular graph with an even number of vertices. So we have something for odd number of vertices, but now let me just give it to you for perfect matchings. Now, the condition that we found for the graph to have a perfect matching is in terms of the third largest eigenvalue. So if lambda 3 of gamma is less than something that we call theta, which is about 2.855, and this theta is the largest root. I'll show it to you in a second what it is, of a cubic, x cubed, so I don't have a closed formula, minus x squared minus 6x plus 2. So this is if d equals 3. And then there are two conditions. One is for d greater or equal to 4 even, and one obviously for d greater or equal to 5 odd. So if lambda 3 is the most this value, or 1/2 d minus 2 plus square root of d squared plus 12, or 1/2 d minus 3 plus square root of d plus 1 squared plus 16, then gamma has the perfect match. And these numbers look a little bit, yeah, I'll tell you in a second where they come from. But this also, what we prove is that these numbers are best possible. So for each of these cases, d equals 3, there is a graph that has lambda 3 equals to theta, which is not going to have a perfect match. And that graph, I can show it to you right now. It's this graph. So this graph, I show you that it has a perfect matching. Exercise number 25. 26, I'm sorry. Yeah, it's good to be ambitious. Find the eigenvalues of this graph. So, you have one vertex, 3 vertices, 12 vertices, 16 eigenvalues. How hard can it be? Okay, I can give you one of them, 3. So 15 eigenvalues. So yeah. So yeah, try to do that. Let me see. Let me give you. I have in the paper. We have pictures of all these graphs for. So I'll tell you first about the examples, and then I'll tell you how the proof works. A little bit of a sketch, and then we can finish up for this part. So this is for d equals 3. And let me give you kind of the idea. So this theta stuff, that theta will actually end up, theta will be the largest eigenvalue, lambda 1 of this graph. And if you want to know where the cubic comes from, if you look at this graph, you have one vertex here, you have 2 vertices here, you have 2 vertices here. This partition is equitable. And if you calculate the 3 by 3 matrix, you'll get the characteristic polynomial, you'll get that cubic. Okay. So the largest eigenvalue of this graph, it appears here 3 times. So think about also something about like, if I take if I just remove this vertex, I have an induced subgraph which consists of three things which are the same. So try to apply Cauchy interlacing and see what it gives you. So, okay. I gave you, too many hints, but okay. So for b equals 4, the graph looks similar, but you have two vertices here, and what you will have here, you will have the following. You'll have 4 copies of the same graph. Uh, in this case, it's just a k5 minus an edge. And then you pair these two things up, and then you do the same thing. And you pair these two things up. Oh, here. Here. So this graph, I claim it's for regular by inspection. So this will be, so each of these graphs is k5 minus you delete this edge. Okay. So k5, everybody had degree 4. I delete this edge. These 3 vertices still have degree 4, so they're fine. These vertices here have degree 3. But for each of them, for each one, I do this, I match them up to here. So now they're degree 4, now they're degree 4, now they're degree 4. And these also have degree 4. So this is for regular. So what you have to show here is there are 2 things. So one, that this graph has, this gamma has no perfect matching. So you can use Stut's theorem, so you can find some set S, it's kind of staring you in the face what S would be, such that the number of odd components is strictly bigger than the cardinality of S. And then the second part is to calculate lambda 3. Lambda 3 will be this, this value that I gave you there. So this is D even, so it should be half. And if D is 4, you calculate what you get there. So it should be 2 plus square root of 28. So I'm doing all the work for you, 1 plus square root of 7. There you go. You just have to prove it, okay? So it's kind of equitable partition, you know? I state the result and you guys can prove it. So, okay? And the one for odd, so this is how the even ones, the odd ones will have kind of a similar structure. It's just what you put here, it's a little bit different, but it's the same idea. Now, let me tell you quickly how we proved this and then let you go. So as before, to prove this, and this was, the idea was in the paper by Brouwer and Hammers, if lambda 3, then gamma has a perfect matching. So what we proved is if gamma doesn't have a perfect matching, then lambda 3 is less than or equal than these things. Okay? Or no, greater or equal, sorry. Greater. Yeah, greater or equal. Okay. So let me draw this picture again. So because gamma doesn't have a perfect matching, this theorem tells you, so this is a condition for having a perfect matching. If you don't have a perfect matching, it means there is an S such that this doesn't happen. So there is an S such that, okay, I have S here. Let's say cardinality of S is here. And okay, I have the even ones here, the even components, but I'm not interested in them. Okay, I'm guaranteed that the number of odd components It has to be what? It has to be strictly greater than S, and it's going to be greater or equal to S plus 1, and there is some parity argument that you can actually prove that is greater or equal than S plus 2. Okay? So here, you have cardinality of S, and you have more than S plus 2 components, odd components. So what you do is, the idea is that you have to argue that some of these components are going to be dense. They're going to have many edges in them. And how do you do that? Well, the number of edges, so you pick here, T1 is a number of the number of edges between the first odd component and S. T2 is this one. TQ plus 2 is this one. Okay? So now, if I add up the number of edges, T1 plus TQ plus 2, so for sure, each of these Ti has to be greater or equal to 1, because they have to be connected. What do I get? Well, I get the number of edges between S and the odd components. But now, how big can this number be? The largest it can be is when every vertex from S sends all these edges down. So this is at most, cardinality of S is S times D, most D times S. So this is not, this is Q, okay? So everybody follows? So if I add up the edges between this component and this one, this and this one, this and this one, what do I get? I get at most, I get first actually the number of edges between S and all odd components. And how big can that be? Well, a vertex from here can send, the worst thing is if it sends all its edges down, and that will be D edges, and you have S vertices. But now Q is going to be greater or equal than S plus 2. So you have more than S plus 2 terms that add up to at most ds. So here it's a multiple of multiple of d times s, but the number of terms it's a little bit more than s. So from these two conditions, you can prove that, let's say there are three t's, t1, t2, t3, that have to be strictly less than d. You have at least three, because if you didn't, if you have if you have at most two that are strictly less than D, then the remaining ones all have to be greater or equal to D, and you will get a contradiction here. And now, when you have something that is less than D, it means that inside here, you will have large average degree. And what we did is, well, this was also in the Brower and Hammer's paper. You look at these three components that have high average degree, and these components are disjoint. So you use Cauchy interlacing to say that lambda 3 of the big graph is going to be the lambda 3 of these three components. But these components are disjoint, so the spectrum of this graph is the union of their spectra, and lambda 3 is going to be at least the smallest, largest eigenvalue of one of them. And that's where these numbers come from. We figure out the smallest value for those. That's why here, for example, this theta is going to be the largest eigenvalue of this graph. And actually, for this graph, this value is going to be the largest eigenvalue of this graph. That's where it comes from. Okay. Okay, I'll stop here. Thank you for being so kind, for listening to me. So we'll continue in a half an hour. Thank you. Okay, welcome back, everyone. So it's before lunch. So thank you for being so patient and listen to my lecture. So today we'll do something a little bit lighter. That is some question that seems a bit like a game that you can go and play with when during the class or when you go home. So what's the idea? So first, let me start with an example. If you have the graph C5, um, and if you look at the complement of it, which is this one, you know that this is also C5. So these two graphs are isomorphic. And if you put them together, so I'll abuse the notation and I'll say plus. What do you get? You get K5. So this I'll write something in this kind of not so formal notation. 2C5 equals K5. Okay. So this is C5. The complement of it looks like this, and it's isomorphic to C5. So you can play this game with other graphs. Okay. Now I have two graphs that we can try to play this game. Let's try these graphs. Now this graph, I want to take copies of itself, isomorphic copies of itself, put them together and see on the same vertex set and see if I get something nice. Now it's going to be very difficult for you to take copies of this and put it together and to get K4. Okay, so try it, but you will get multiple edges right away. Okay, no matter what you do it. But if you rotate this vertex around, so if we move this vertex, what do we get? So if we pile up all these edges together, every edge of K4 will appear how many times? Twice. So you get 2 K4. So this is a game I want to play for various graphs. So we take C5. Can take put two copies together. I get a K5. I take this graph K13. I put 4 copies of it together, and I get 2K4. Now let's jump to something much bigger, which is again, and I don't know if you're familiar with this problem, but let's see. So this is our friend the Peterson graph. Okay. If I am in the graph K10, 10 vertices, and I take away the Peterson graph, what am I left with? Peterson is 3 regular, so I'm left with a 6 regular, which is the triangular graph on T5. Can I find another Peterson in there? So this kind of, if you see it first time, will take you by surprise. But let me give you, I have nicer pictures. I'll tell you in a second where you can find them. So let's see. So this one goes into the complement. So I'll go like this. And I'll go this one here. And then you kind of rotate that type of thing this way. This one will go here. This one will go. Where does it go? Yeah, all the way to the top. And this one goes here. So this is Peterson. Now, we haven't talked about it. Peterson, we kind of define it by a picture, but you can also think of it as what? As what is called a Kneser graph, Kneser K52, in which the vertices are all I will write it like this, all the 2 subsets of a set with 5 elements, and 2 of them are adjacent. So AB is adjacent with CD if and only if, they put it up, if and only if they're disjoint. So here, let's try to label the vertices. I'm not going to use the curly brackets. I'll just use it as words. So for me, 1, 2, this will be the same thing as 1, 2, but to make it easier, okay? So I claim that the Peterson graphs, the vertices, you can label them by the 5 choose 2 pairs or 2 subsets of a set with 5 elements. 5 choose 2 is 10, such that you have an edge here between 2 pairs if and only if they're disjoint. So you have 1, 2 here, and you can do 3, 4, 3, 5, 4, 5. And now if I pick one more label for a vertex, it kind of pretty much will determine everything. So 3, 4 has 1, 2. So the other neighbor should be 1, 5 and should also be 2, 5. So I'll put here 1, 5 and I'll put here 2, 5. And then you will determine, so here 1, 5, 4, 5, what should be here? Disjoint from them. 2, 3. 2, 5, 2, 3, what should be here? 1, 4. 2, 5, 4, 5. 1, 3. 1, 3, 3, 5, 2, 4. So that's kind of how you can come up with this on your own. So it works. 1, 2, you know, 3, 4, 3, 5, 4, 5. You pick another one and it kind of fills it up itself. Okay. So exercise number 26, 27. Okay, don't try to trick me. So show that this is also Peterson. And you will see that this Peterson and this Peterson have nothing in common. Okay, so I put this Peterson. I don't know if you have this kind of. I don't have this kind of X-ray vision. What is left there? It will be, you have a 3 regular. You can probably see from the picture that there will be no overlap of edges, and you will get, when you take what is left, should be another 3 regular. Is that Peterson or not? We don't know. Well, I can tell you that it's not going to be Peterson. So what I'll show you now, this is a famous result in algebraic graph theory, spectral graph theory. You can find it in Gottsiel and Royal book. You can find it. There's a very nice book published by the MS called 33 Miniatures in Mathematical and Algorithmic Applications of Linear Algebra by Jiří Matušek. And this is one of them, what I'll show you here. And also, I'll tell you in a second that where you can find more recent information about a paper that I wrote with Peter Cameron about 10 years ago. But now, what I want to prove is that on the same vertex set of 10 vertices, you cannot find 3 disjoint Peterson graphs. You cannot pack 3 disjoint Peterson graphs. So 3 Peterson graphs cannot equal K10. So I'll write it in this form, and I hope the meaning of it is clear. So again, here you see 2C5 equals K5. I take 2 disjoint copies of C5s, edge disjoint copies of C5 on the same vertex set. I put them together, I get K5. 4, this one is 4K13 equals 2K4. I take 4 disjoint copies of edge disjoint copies of K13. I get here 2K4, each edge of K4 twice. And here I'm saying that I'm claiming first that you can find 2 copies of Peterson, that are edge disjoint on the same vertex set, modulo exercise 27, which you have to prove to convince yourself that this is the Peterson graph. So essentially, you have to give label the vertices such that it looks like Peterson graph. But what I'm trying to say is that you cannot take 3 such that you can make a K10. And this is what kind of a statement? You see any eigenvalues here anywhere? It's a combinatorial statement. It's about the graphs that you cannot pack them together such that you get K10. Okay? So I'll show you the proof. Let me give you a little bit of the history. Okay, so this problem was posed by Alan Schwenk in American Math Monthly in 1983. And I'll give you in a little bit, like you can find more about the history, about the history of this problem. Like I said, I have a paper with Peter Cameron, myself. It's in American Math Monthly. When is this? I think 2015. It's called a graph partition problem. In which we give a little bit the history of this problem, and we kind of extend these results to other graphs and so on. Okay. Okay. So now let me give you the how do we prove that 3 Peterson doesn't equal a K10? So you prove it by contradiction. So assume that 3 Peterson equals K10. So what exactly does it mean? It means that there are 3 edge disjoint copies of the Peterson graph that when you put them together, you get K10. Now, one thing you should realize is that when you talk about decomposition of graphs, like in this case, it's edge decomposition. The vertices are the same, but somehow these copies of Peterson are edge disjoint. Edge decomposition works very well with adjacency matrix because edge decomposition or partition, it's the same thing as adding adjacency matrices. Okay, so so assume 3 Peterson graph is this. Let's write that more precisely. Assume that there are 3 graphs. Let's call them P1, P2, P3, each isomorphic to the Peterson graph. And now so they're on the same vertex set, such that the edges of P1 union the edges of P2 union the edges of P3 equals the edges of K10 on this vertex. That's what I mean about decomposition. Okay, so I didn't write on the same vertex set, but I just said it. Okay. Okay, so now, okay, what does it mean? So because this is, so again, because you have EP1 disjoint union with EP2 disjoint union with EP3 equals the edge set of K10, that's actually the same thing as if I take the adjacency matrix of P1 and I add the adjacency matrix of P2 and I add the adjacency matrix of P3, I have adjacency matrix of K10. That's equivalent because there's no overlap, so nothing, no two ones are going to go together. Okay, so I want to get something bad happening from here. Okay, now what do we know about Peterson graph? Peterson graphs, that's the thing about spectrum. Your graph may have a different labeling. You know, the adjacency matrix may look differently, but all these copies of Peterson graph are similar to, so they have the same eigenvalues. So the Peterson graph or the same thing like also P1, P2, P3. The spectrum is 3 with multiplicity 1, 1 with multiplicity 5, and minus 2 with multiplicity 4. We did this earlier, okay? Sometimes, you know, people are excited about what we're talking here. So, yeah. So now what we're going to focus on is on this one that has large multiplicity, has multiplicity 1. So I will denote by V1 is the eigenspace of 1 corresponding to the graph P1. Okay, V1 to P1. It happens that it's also 1, but the same thing, V2 will be the eigenspace of this corresponding to P2, and V3. Okay, so from here, well, first let's look at the space. You have here R10. So you're gonna have here V1. I don't know how they overlap. V2, V3. Clearly 0 is here. Okay. Um, one thing is short. Dimension of V1 equals dimension of V2 equals dimension of V3 equals 5, because that's a multiplicity of 1 for each of them. Okay. And initially you say, okay, they live in a 10-dimensional space, but you know they actually live in a 9-dimensional space, because the eigenspace here, you know for sure it's going to be orthogonal on the all one vector. And the all one vector is the same for P1, P2, P3. This other one here, you can say, okay, my V1 is also orthogonal on this eigenspace, but this eigenspace is maybe different for P1, P2, P3. But all one vector is all one vector, no matter how you look at it. And so the all one vector is going to be here. So these spaces, these things live in a 9-dimensional space. Okay, so V1, V2, V3 are subspaces of one perp. You're not convinced? Eigenspaces for different eigenvalues are orthogonal. So this eigenvalue 3, for V1, its eigenspace is all one vector. For V2, its eigenspace is all one vector. For V3, its eigenspace is also the all one vector, no matter how I label the vertices. For P1, maybe P1 is labeled this way. I will have some kind of eigenspace V1. If I look at P2, which is maybe this one, the eigenspace looks different. But the one for 3, it's always the same. And all of these V1, V2, V3 are orthogonal to the all one. Okay? Okay. Now you make kind of sense where we're going, because I made such a big deal that V1 and V2 and V3 are in a 9-dimensional space and they have dimension 5. So it's kind of like you should have some kind of sense that, okay, something is happening, you know? So what is happening? You have dimension. So because of these things, you'll have dimension of V1 intersect V2 equals dimension of V1 plus dimension of V2 minus dimension of V1 plus V2. This is 5 plus 5, but dimension of V1 plus V2 is at most how much? 10, but now we just argue that it's at most 9. Yeah, so this is greater or equal than, so you get 1. So no matter how you twist and turn your two copies of Peterson graphs, their eigenspaces will have something in common. That's basically it. So therefore, there is U belonging to V1 intersect V2, U is not 0. Okay, so just any two of them will intersect. It doesn't mean that all of them will intersect non-trivially. So I'm guaranteed that two of them, this is here, this is where 0 is for sure. 0 is in all of them. Okay. Yeah. Okay. So now what do we have? We have that this equation, we multiply everything by U. So what we'll get is AP1 U plus AP2 U plus AP3 U equals AK10 U. No, yeah, thank you. Yeah. Okay, so which one do we know? U1 comes from V1 intersect V2. So how much do I get here? U, because it's eigenvalue 1. So here, because U belongs to V1, I have U. Here, because U belongs to V2, I also have U. Here, I don't know, so I have AP3 U. What do I get here? U is in V1 intersect V2, which are inside the orthogonal complement of 1. What is this? This is J10 minus I10 times U. J10 U minus U. How much is J10 times U? It's going to be 0. So you get minus U. Okay. So now what do we do? You just go after this one. So you get AP3 U equals minus 3U. So, 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 okay, that's what I mean. So, because Peter's, well, actually, what this tells you is that, so of course you can, this implies that P3 cannot be Peterson because Peterson doesn't have minus 3 as an eigenvalue, but it tells you that if you take two Petersons like I did here and I put them together, what you will get actually, it will be a connected graph, and it will be a graph where the least eigenvalue is minus 3. So that graph will actually be bipartite. So you can look, there is about this problem, there is a combinatorial argument. I don't know if you guys, do you use math overflow? So math overflow, I mean, many students, when they cannot do their homework, they go and ask you there, but there's nothing, yeah, okay. I won't comment on that, but you look up and see about this question, and there's some kind of combinatorial argument that if you put two Peterson together, if they pack together, what is left is always going to be bipartite. Okay. That's a very good question. Exercise 28. Yeah, you can look on Math Overflow and you can see. Okay.
3 Peterson not equal to K10.
Yes.
But it can be 6 Peterson equal to.
Very good question. So look who wants to do more work. So if you look in this paper, you can actually see that we have that 6 Peterson equals 2K10. So that is true. And even crazier, 9 Petersons equals 3K10. And once you get 2 and 3, you can get 4 because you can repeat this. You can get 5 because you can put this together. You can get anything. It's just 1, it doesn't work. So this problem we study in this paper where maybe it doesn't work, like Peterson, it doesn't work, but you can, let's try to make a multiple of K n in general, and let's see something with as small as possible. So that's what we study in this paper. Okay, so you can play this game. I think we have some open problems, but I won't go there now. So, but I figure this is, again, something to keep in mind. Again, the message here is that whenever you see something about edge decomposition, that will play well, and I'll give you an example in a second, another example, that will play well with adjacency matrix, just to be a sum of adjacency matrices of smaller things. And then you can try to do some linear algebra, okay? That's, yeah. Okay. So then I'll tell you about a different problem. So this one, you can call it graph addressing. So let me tell you what I mean. So for this problem, the origin is in the work of Ron Graham and Henry Pollack. in the 1970s. You can find a couple of papers online, and they were working at Bell Labs. And so their thing was, okay, you give me a graph gamma. So for our purposes, something small like this. Okay, maybe. But think about it, nowadays we have graphs that are large and so on. Even that time they were large graphs. What do we want? So the goal is to find some kind of function, or so this is they call it addressing. So which is a function from the vertex set of the graph to some kind of alphabet of some length. Let's call it m. So these are like words of length m over some alphabet, such that if you give me two vertices x and y in V, one can figure out the distance in the graph between x and y and a shortest path from x to y by investigating by looking at f of x and f of y. So you have these addresses. So you want to put some kind of addresses or labels on the vertices that if you give me two vertices, I can just look at their addresses and I say, okay, the distance is this much, and this is how you go from there to there in a small place, in the smallest time. Let me give you just a small example. Let's try this one. So this one is for the cycle C4. So the simplest, the first attempt will be to try A to be just 0, 1, like a binary words. Okay, and you can try. Okay, how would I want to do it? Maybe I would like to do it with binary such that the distance in the graph between x and y is the Hamming distance, the dh between f of x and f of y. So the Hamming distance is the number of positions in which the words fx and fy have a different coordinate. Okay, so here it works. You can do 0, 0, 0, 1, 1, 1, 1, 0. And you can see for any vertex, any two vertices and so on, it works. It works for even for bigger graphs. And this will work. You can do it with a binary 0, 1, if and only if the graph is what is called isometrically embeddable into a hypercube, into a cube that maybe this is a cube of dimension 2, but they're cubes of dimension 3, 4, and so on. We'll talk about them maybe in a little bit, but how can you get the cube of dimension n? One way, you take two copies of qn minus 1, qn minus 1, and you put a perfect matching between them, or you can just designing from scratch. The cube of dimension n consists of all the words, binary words of length n, two of them adjacent if they differ in exactly one position. So okay. So this works, but for example, you could have a graph like this, like a triangle. So for the triangle, if you get stuck with the addressing with 0 and 1, because you can give this 0, you can give this 1, you're okay. There are addressing in which you can use more letters. So if I'm using 3 letters, I could give this 2 and I'm good. So that works. But if I'm just using 0 and 1, what do I put here? Well, maybe it doesn't work with length 1. So maybe I add another letter. So I do here 1, 0, 0, 0, 0 here, and maybe I put a 1. So now this is okay. This is okay. But I have a problem here. So no matter how you want to increase the length, this is not going to work. This will not work over the alphabet of binary. So binary works for this class that I told you about, something that I call isometrically embeddable in the hypercubes. Yes?
If you want it to be the Hamming distance.
Yes. That's a very good point. So that's a very good point. So this is if you want exactly to be the Hamming distance. There are different addressing. So um, there's a survey about this, and I don't remember the title of it, but about graph labelings, in which you want to get the distance between two vertices from their labels. But okay, it doesn't have to be like the Hamming distance. Maybe there's a different formula that I can use to get the distance, and the problems are different there. But for this type of question where you want the distance to be the Hamming distance, it doesn't work. Okay. So what did Graham and Pollack do? They came up with another type of addressing, which is, I'll describe it now. So the Graham Pollack, so you will have a function. They introduce another character, 0, 1 star, but it's a, let's put here M. So you have words over the alphabet 0, 1 star. Okay. And this star can be at the same time. I mean, it's not a quantum thing to be at the same time in two positions, but this star can be at the same time a 0 as a 1. And so what I'll show you, what they figure out is that you can find for every graph, there is an F like this, there is an M like this, such that the distance in the graph between X and Y, so for any XY, I'll put it, for any XY in the graph, the distance in the graph between X and Y equals the numbers of positions J, where if I look at the label of X in position J, and if I look at the label of Y in position J, one has a 0 and the other one has a 1. So for this count, only the positions where the star is not taken into consideration. You can say, well, if the star is not taken into consideration, how does this work? Well, it will work. Let me show you. So they prove that for any graph, you can find a function such that the labels are words over the alphabet 0, 1, and star, such that for this happens for any X, Y in V. So let me show you how this would work over the triangle. So let me erase here. We'll get to that. Don't hold that thought, because I'll give you many problems about this. So don't worry about it. So here, if I'm using, so it didn't work with binary. Now let's say if our alphabet is 0, 1 star. As before, maybe I do 0, 0, 0, 1. I'm okay here. I put a 1 on the first position. It makes me okay with this. And then I put a star on the second position. So all the distances in this graph are 1. Okay, that's easy. So we just have to check the right-hand side for any two vertices. So if I look at 0, 0, 0, 1, the second position, 1 has a 0, so it's 1. It's okay. Now, let's look at 0, 0, and 1 star. On the first position, 0 and 1. On the second position, 0 and star, but that doesn't count. So if you want to think about it, in this situation, the star acts as a 0. The star acts as a 0, and it doesn't, it doesn't contribute to anything. Now, let's look from here to here. In the first position, 0, 1. In the second position, I have a star, but the star here now acts as a 1, and I don't have anything. So it works. Another way to think about this is, and you will see, it's kind of like a squashed cube. So I have, this is my cube Q2, the two-dimensional cube. And I have 0, 0, 0, 1. And here I have 1, 0, I have 1, 1. Okay, that's the labeling with that's the usual labeling with 0, 1. So when I squashed, I take these two vertices and I squash them. So I combine these two vertices into one. Wherever I have the same entry, I keep it the same. Wherever I have different entries, I put a star. And that's how you can think about the squashed. You can squash even bigger cubes. So like if I give you this cube 0 0 0 0 0 1 0 1 0 0 1 1, what do I have? 1 0 0 here, 1 0 1, 1 1 0, 1 1 1. You can pick any, like an edge is going to be a cube q2 q1, a c4 would be an, so you can squash whole thing. Like I can squash the whole thing here, and what do I get? I will get this part stays the same, and it will be something adjacent to here. So this one will be zero. Yeah, maybe I can I squash? Yeah, it will be star 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 1, because you have a 1 in the end and you squash everything. Okay. So there are several questions. So question 1, is there such thing for every graph? So we'll prove this in a second. So for any graph, and this is what Graham and Pollock proved, for any graph gamma, there is f from the vertices to 0 1 star m, for, I'll put here some m, such that this thing happens. Okay, so I'll show you first that. Second, once you know this, that for any graph this works, you are interested in the smallest such a value. So we denote by n gamma, it's the minimum of m. Okay, so the smallest length of an addressing. And we can ask ourselves, well, what can we say about this? What is, for example, n of kn? What is the smallest length of an addressing for the complete graph? Like here, for example, I showed you this is an addressing of length 2. So the picture tells you that n of k3 is less than or equal to 2, because I have length 2. And I showed you earlier that you cannot do it with 1. So that's that. But now, what is going to be? What if you want to do this?
Squash one more.
Eh?
Squash one more.
Oh, he wants to squash more things. Yeah.
Okay.
Yeah, no. I think you're on the right path. So let me give you first this one, show you how this works, and then we'll talk about the second part. But this is something you can think about this for any graph. First I'll show you why this is true, and maybe that will help you to try to understand what happens with this n gamma. Okay, so let me erase here. So for the proof, maybe it's good if I have an example. So let me think about an example. Let's think about something small that is not a triangle. So I will show you how an addressing here, so something here, addressing, is equivalent to something else. So, okay. So for the first part, here's what we're going to do. For for gamma, so gamma is a graph, so it's a simple graph. From it, I'm going to create what is called the distance multigraph. The distance multigraph of gamma. It will be a graph in which you have multiple edges, but no loops. So, and the vertex set, so this one, let me call it fancy D, or D of gamma. The vertex set of fancy D is the same thing as the vertex set of the graph. And the edge xy in here has multiplicity equal to the distance between x and y in the graph. So if x and y are equal, the distance is 0, so I have no loops. If x and y are adjacent, so like let's see in the picture. If this is gamma, this is d of gamma. If I have here x and y are adjacent, then the distance between them is 1. So here it just copies the same picture. X and y are the same. Okay, but if let's say y, I have y and this is z, so this is a distance 2. Then between y and z, I will put two edges. So let's do it here for this graph. So this is a graph gamma, and then if you look to the distance multigraph of gamma, wherever you have edges, you keep edges, but you have a pair of vertices which are a distance 2. So then you add a multiple edge. There is one graph where the distance multigraph is the same thing as the graph itself. Complete graph. So very good. So remember, yeah, distance multigraph of Kn, it's the same thing as K. Very good. Okay, this. So let me erase here. So I'll keep this example maybe here. So this is gamma, distance multigraph of gamma. And let me label this 1, 2, 3, 4, 1, 2, 3, 4. Okay. So now what I want to show you is the first part. And the first part is an if and if only if condition. So it's the following. There is f from v to v0, 1 star m such that distance between x and y equals the number of positions j, where Lx of j, Ly of j, 1 is 0, 1 is 1 for any x, y in V, if and only if there is a decomposition or partition of the edge. I mean, you can call it multiset of the distance multigraph d gamma into what we call bicliques, which are complete bipartite subgraphs. Bicliques. So, which one?
In the definition, such that the distance is equal to
Number of j where f. I changed it to L. Thank you, f. There is a decomposition of the edge multiset into m, exactly m complete bipartite. So let me show you the implication from this decomposition back. So a complete bipartite subgraph, a complete bipartite graph, you know what it is. It's two vertices and you put all the edges in between them. and I just call them bicyclic. So now let me do here, let's start with this. Let's try to decompose this into bicyclic, and then I'll show you the recipe of how you find the addressing. Okay. Now, bicyclic edges are bicyclics, stars are bicyclics. So if I want to decompose it, maybe I want to use all the edges here. So I want to take as big as bicyclics as I can. What are the biggest that I can take here? It's K22 or C4 probably. Okay. So here, let me take, so for this one, let me take one which is like this. So I take 1, 4, 2, 3. Does everybody see? And then can I do it with what is left? So this one, how many edges do I have in here? I have 7. I just I took care of 4. So there's 3 left. There's the 2 diagonals. Can I do it? Which one? So no, there's 1 diagonal that is left, just 1 diagonal that is left. So I can take care of this one, 1, 3, and maybe I take it with 1, 2. And then there is one more. What is left? 3, 4. Okay. Okay. So let me give you the general recipe here, and I'll do it over there for this example. So when I have a decomposition, so this is the implication this way. So assume that this D of gamma is some bicyclic B1, which has this X1 and Y1 are the partites, are the color classes, union blah blah blah, union B XM YM. So for example, here in this example, X1 could be 1, 2, and X2 and Y1 would be 3, 4. And my bicyclic is this 1, 2, 3, 4. Okay, I could label them the other way around. Yeah, that's possible, but won't affect things here. Then the second one is 1 and 2, 3. Again, I can say X2 is 1 and Y2 is 2, 3. So you see these bicyclics are not spanning. They don't have to be spanning. The first one is spanning, this one, it doesn't have to be spanning. And the last one, what is it? 3, 4. Let's go crazy and we change the order. This is 4 and this is 3. Okay. So now I want to come from these things. I want to come up with a function from the vertex set to 0, 1 star. The number of this is m. In this case, I want to put 3. So I want to put a word for each vertex of length 3. Okay. So here I have f1, f2, f3, f4, and these labelings will be corresponding to each one of these bicyclics. This is the one x1, y1. This one x2, y2. This is x3, y3. Okay, so what's the rule? How do I assign these numbers? The rule is following. So define f from v to 0, 1 star m, f of x in the position j equals, so x is a vertex, j, it goes through one of these things. Okay, so what I'll put is I'll put a 0 if my vertex x belongs to x of j. I put a 1 if my vertex x belongs to y of j, and I put a star otherwise. Okay, so let's go here, f of 1. You look in the first one, where is 1? It's 1, 2, so I put a 0. In the second one, it's also in the first part, so I put a 0. In the last one, there's nowhere there, so it's a star. And you do the same thing. 2. In the first one, it's here, it's a 0. In the second one, it's in the second, so that's a 1. And it doesn't exist in the last, so it's a star. F3, in the first one, it's a 1. It's also a 1 here. And it's also a 1 here. And the last one, F4, it's a 1. It's a star. And it's a 0. Okay, so you say, so what? Well, what I claim now is that if I look at any two vertices here and I look at the distance between them, it's guaranteed to be the number of positions where one is a 0, one is a 1. So let's pick 1 and 2. What's the distance between 1 and 2 in the graph? 1. And what do you see? What is they differ in exactly one position, but look, what is that position? What does it correspond to? It corresponds to x2, y2. x2, y2 is the only biclick where the edge 1, 2 is actually captured. Because the edge 1, 2, you don't get it here, you don't get it here, it's only here. So that's the idea. Now, let's do 1 and 3. F1, 1 and 3 are a distance 2, and they differ here and they differ here. So look at the first one. It's 1 and 3. 1 and 3, you get it in this biclick. Look at the second one, 1 and 3, you get in this biclick. So that's why you have the ones, you have these discrepancies on these first two, and then in the last one, you don't have. Okay, so I won't give you the proof, but this works. So this is an if and only if, and this is a recipe for finding an addressing. I mean, you can work directly with an addressing, but you can work with this biclick decomposition and so on. Okay, so far it's a combinatorial problem. This labeling, this addressing becomes a decomposition. Okay, so try it for some graphs just to see what you get. So now let's go to the one of the graphs that I told you, the graph, complete graph. So for Kn, complete graph, you have that d of Kn equals Kn because all the edges are there. So the distance multigraph is the same as it. So by this theorem, an addressing of Kn of length. So I'll put this m is called the length of the addressing of length m is equivalent to a partition of the edge set of Kn into m biclicks. So in general, for a general graph, an addressing of the graph, it's equivalent to a partitioning of the distance multigraph. But for Kn, the distance multigraph, it's the same thing as the multigraph. So then this parameter n of Kn becomes the minimum number m such that the edge set of Kn can be decomposed into m biclicks. Okay, so what is it? That's log is for cover. Here, so what did we get? Let's try for example, so we saw earlier nk3 is 2. Let's try 1, 1, 2, 3, 4. Can you decompose this into biclicks? They don't have to be spanning, okay? 3? Okay. I'll just... Do you want to use a big star or... So, okay, let me do it with big star. K13, center at 1, then plus the one center at 2, plus the ones 3 and 4. So this is, they're all, so NK4 less than or equal to 3. Because it's a minimum. Can you do it with 2? By this argument, you see, like this construction, you can generalize it for Kn, because you take Kn, pick the first vertex, take the big star there, then you take the star. So this argument, you have NKN it's less than or equal. So let me give you the idea of what happens for Kn, and we'll talk about the general case after lunch. So what do you think? Are we done, or do we have to do something? Okay, let's see for NK4. Could this equal to? Could you do it with 2? I mean, you could do it by a case analysis. That okay, if you have K4, you have to take care of how many edges? 6 edges. What's the biggest? If you want 2 biclicks to cover 6 edges, one of them is going to cover 3 or more. So if you're covering 3 edges, you have to be K13. If you're covering 4 edges, you have to be K22. And in each case, if you're using a K13, you're left with a triangle, so you're stuck. If you're using a K22, you're left with 2 disjoint edges, so you're also stuck. So it doesn't. But how is it going to work in general? If I give you now NK of 5 or 6 or so on, can you know? So that's the difficulty. And this is actually a theorem that NKN actually equals n minus 1. Now, here's a question for you. So I gave you here one partition of K3 in this, and there are many partitions. So when you prove NKN is less than or equal to n minus 1, you're using a partition of Kn into n minus 1 biclicks. And there are many such partitions. So I showed you this one here, but you can do even for K4, you can do a different one. You can start with a C4 first, plus you use one edge, the edge from the left, then you use the edge from the right. And in general, you can start, you have your graph, you can start with the part A, part B, you take everything, and then you see what happens inside it. So there's an exercise, and I don't know if anybody has done it, but I think there is this book called by Babai and Frankel. You can find it online, I think for free. It's the PDF. It's called Linear Algebraic Methods in Combinatorics. And they have an exercise that there are at least 2 to the n minus 4 such partitions of Kn. I don't know if it's you label, you have to pay attention, but there are. So there's not, I don't know if anybody has looked at, this might be a good project to look at actually the exact number and try to figure it out. The exact number into, how many ways can you partition Kn into n minus 1 biclicks? Because now you have online encyclopedia of integers, so if you get some numbers at the beginning, you can maybe guess what it is and so on, okay? But now, here it's a different problem. I want to prove, so this one is essentially the same thing as NKN greater or equal to n minus 1. Because I already have less than or equal to n minus 1 from construction, and I want to convince you that this is true. So this is a proof that is done in a paper by Tverberg in Journal of Graph Theory in like 1980s. It's like a one-page proof. So here's how it works. Assume that nkn is some number, let me call it t, which is less than or equal than n minus 2. Okay. Let's say somehow for n 100, you can make it with 98 biclicks. You have some kind of magic and you can do it. Okay. So what do we mean? It means we have this x1, y1, xt, yt, all these biclicks. So here you have x1, here you have y1, boom, 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 and here you have xt, here you have yt, and so on. Okay. So I have this kind of decomposition. These things together give me all the edges in K10, Kn. Okay. Questions? So this T is at most n minus 2. It will come into play. No, for now it hasn't. It hasn't. We're just setting up the scene before the drama begins. Okay. So now what I will do is the graph. It has vertices for me are 1, 2, 3, blah, 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 n. I will associate some variables. Because I use x, I will use z1, z2, zn. Okay? So the fact that the edges in the graph decompose in all these biclicks is equivalent to the following. The edges in the graph, so on one hand, I will have edges in Kn, but if I write it in terms of variables, the thing corresponding to it will be something like summation for all ij, I less than j less than or equal to n, zi, zj. Okay, so I can think about the edges in terms of the indices of this in this product. Ij cover all the edges in Kn. Okay, now this one is going to be decomposed in all the edges of x1, y1, blah blah blah, xt, yt. So what it means is that this expression will equal summation. Let me see if I can put it here. Summation over all. Let's say L from 1 to T, of the sum of the vertices A in the part XL, ZA, times summation over the vertices B in the part YL in the ZB. So here, the notion of a set being decomposed, being partitioned in these sets, becomes here a sum in which each term of the sum correspond to an edge from the graph, and every product zi zj, I will find it in one of these things because the edge ij belongs to exactly one of these things, and at some point I will be in xl and j will be in yl, or vice versa, and I will catch it there. Okay. So the problem about the edge decomposition, it can be rewritten equivalently in this type of algebraic form. Okay. So nothing. This is, again, we haven't come to the drama yet. We're just setting up the scene. So and now here's what we're going to do. We're going to consider the following linear system, a linear system. Well, no, system of linear equations. Linear equations in variables z1, z2, zn. So I will have the following, the sum z1 plus zn is 0. And for any I from 1 to, no, for any, let's say L from 1 to T, summation, or one of these things is 0. Summation of A in XL of ZA is 0. Okay, so how many variables do I have? Huh? N variables. How many equations? One equation and T plus one equations. And what did we assume about T? So T plus one at most N minus one. So I have more variables than equations. So you're supposed to contribute next. There is a solution which is non-zero. Very good. So from here, there is a non-zero solution. I'll just use Z for it as well. Okay. Okay. So I have a non-zero solution. What does that mean? You see, for each L, the sum on this side, this is 0. So it means this product will be 0, which means this sum will be 0, which means this thing will be 0. So from here, I get that the summation over all but you know that Z1 square plus Zn square. So on one hand, this has to be positive because it's a non-zero solution. But this one is what? This is Z1 plus Zn square minus 2 times summation over I less than j less than or equal to n Zi Zj. How much is this? How much is this? So, contradiction. So what's the contradiction? It's about t. T cannot be less than or equal to n minus 2. T has to be greater or equal to n minus 1. Okay? So this is the proof. Again, this is a beautiful proof. It's not quite eigenvalues, but I don't want to put you through more pain to give you the general. There's something more general than this that applies to any graph, and I'll do that after lunch. So I'll show you after lunch, and then after lunch we'll talk about the question that one of your colleagues asked about what happens about minimizing this number m for various graphs. There are many questions there that are still open. Yeah.
System is also getting Z1 plus Zn equal to 0.
What is it?
G1
Yes. Yeah.
The system of equation.
Yes. So my system of equation, I have t plus 1 equations. Well, why am I didn't consider this is Tverberg. Now the idea of it is, so here again, like I told you before, that edge decomposition is the same thing as adding adjacency matrices. Here it's written in another form in terms of this quadratic form. So you have here all the edges of the graph correspond to all the products Zi, Zj, I different than j. So the indices here go through all the edges. We'll see this in the afternoon when I'll give you the general result. And here, the fact that this decomposes into these bicliques and so on is equivalent that this summation here becomes a sum of all these products. Okay, so that's the first thing. So the problem moves from combinatorics, moves to linear algebra by this thing. And now, because t is assumed to be at most n minus 2, now this is, I guess, the genius of the proof. Where does it come from? So because t is at most n minus 2, t plus 1 is at most n minus 1. So you have more variables in equations, So this system has a non-trivial solution. So z1 squared and so on should be 0. And then it should be positive, but it's actually 0. Yeah, you're asking a very good question, Yes, so I'll show you again in the afternoon. I will show you a more general result for an arbitrary graph, which gives you something like a lower bound, and that result will imply this one. So hopefully that one will use this kind of decomposition. It will be a different type of, but also linear algebraic, and you can compare the proof from the afternoon with this one and see maybe that will give you better insight. Okay. But I think I'll stop here because I think, yeah. Oh, you have a question? Yeah. Very good question. That's a very good question. So that's, I will talk about this in the afternoon, but you're right. So, but this is a big result. So in the original thing, paper by Graham and Pollack, when they look at this n gamma, they prove that it's at most the diameter times n minus 1. So that's what they did, okay? At most diameter. And then I think Graham conjecture that this is n gamma is at most n minus 1. And this is the squash cube conjecture. And this was proved by Peter Winkler in like early 90s that this is always the case. N of gamma is at most n minus 1. But I'll give you examples in which is not n minus 1. So that's actually a very good question. So all the time, the n gamma will be at most a number of vertices minus 1. I mean, you see here for the complete graph, it has to be that. But for many graphs, it won't be that. And yeah, that's a result. But if you want more, I'll mention it later. This n gamma, one interesting question that I don't know how to solve is to prove that this n gamma is actually an NP-hard parameter to calculate. I believe it is, but you have to find the right reduction, and I haven't found the right reduction. Okay. All right. So I'll stop here. Okay. So we'll continue in the afternoon. There you go. Thank you. Very nice of them. Thank you. Okay. Thank you. We can start. Okay, so welcome back, everyone. So we'll continue talking about this problem of addressing of graphs that we discussed in the last part. So let me remind you what we are doing. So we have this graph with vertex set V and edge set E, and we want a function from the vertex set to the words of length, some length m over the alphabet 0, 1 star, such that the distance in the graph between x and y equals the number of positions j, where if one of the words has the 0 and the other one has a 1. Okay, and cutting up. So last, and we show that this can always be found. Well, we show that this function, the existence of such function, is equivalent to a decomposition. There is a decomposition of the edge set of the distance multigraph of gamma into this bicyclic, complete bipartite subgraphs. Now, is there always a decomposition of the gamma into bicyclics? So this question is equivalent to this one. Yeah, how can you do it? Edges, every edge is a bicyclic, so you can always do it. So then, with this in mind, this parameter n of gamma is, which is the minimum m, with these properties, this is well defined. Okay, and we show that this result that n of complete graph kn equals n minus 1, and upper bound by a construction, lower bound by a linear algebraic argument. Okay, so again, the question here is, this is open. N of gamma, I believe it should be, it's NP hard to calculate, but we don't know. Okay. So with that in mind, I think someone asked at the end of the previous lecture, what do you know about this N of gamma? So in the original paper, so I wrote earlier at the bottom, let me write it again here. So in their work in the 70s, Graham and Pollack proved for any graph, but so if gamma is connected with diameter d, then this parameter n of gamma is less than or equal. Let me write it this way so that people won't get confused about functions. N minus 1 times d. So that way it's clear that it's a product, okay? And I mentioned Graham later on. He made a conjecture, and this is also known as the squash cube conjecture, that n of gamma is less than or equal than n minus 1. N minus 1 is the number of vertices, okay? And this was proved by Winkler in 1980s. This is a paper in Combinatorica, which is called Proof of the Squash Cube Conjecture. And so he proved that n of gamma is less than or equal to n minus 1, okay? So for any graph is at most n minus 1. That doesn't make it efficient to calculate because n can be any numbers there and so on. And if you want, so you can find the paper, the original paper is like 3 pages or 4 pages. And if you like a little bit like if you like this type of algorithm, like breadth first search, depth first search, and so on, the way he finds an addressing with n minus 1, length n minus 1, uses this type of algorithms about depth first search, breadth first search, and so on. And you can find this proof also. There is this beautiful book called A Course in Combinatorics by Van Lint and Wilson. And the proof here, this proof is, I think, chapter 10 or chapter 9, something like this. It's half of that chapter. They explain it there, how the proof works. So yeah, okay. So this parameter is always the most n minus 1, but for many graphs, we don't know what it is. So let me tell you how the main, so for this parameter n of gamma, if you want to prove an upper bound, so an upper bound, let's say this is at most, I don't know, let's say capital M, what you need is you need a construction. You need to tell me how to put these addresses and so on. So this needs a construction. Now, on the other hand, if you want to prove this is greater or equal, or let's say this is strictly greater than some number, let me call it L, you need to do something like we did for the Tverberg proof, where we said, I want to prove that n of kn is greater or equal to n minus 1. Therefore, I want to prove that, you know, it's, you need to give a proof, essentially. So here you need some kind of proof, okay, or lower bound. Now, again, for construction, this will depend for each problem. There will be different construction for each problem. But for the lower bound, the main tool for lower bound is the following theorem. You have the graph as before. Now, let's do this example that we had earlier with, I forget which way I did the diagonal and which way I labeled things. Let's say 1, 2, 3, 4. Okay, let's say this one was. It could have been the diagonal the other way around. But this is my gamma. From here, I have the distance multigraph of gamma, where I have edges I keep the same, and here I put 2. And from here, I can also create, I mean, I could do it from here directly, but you can also have the distance matrix of gamma, which is I call D, and you have the vertices 1, 2, 3, 4, and you have here 1, 2, 3, 4. And in the entry xy, you put the distance between x and y. So it would be kind of like an adjacency matrix of this. So you have 0, 0, 0, 0, 1 and 2, 1, 1, 1, 1, 1, 1. The only one that's 2 is 2 and 4. So 2, 4, and then 1, 1, 1. Okay? So that's a distance matrix. So the theorem here says that for any graph, n of gamma is going to be greater or equal than the maximum of the number of positive eigenvalues of this matrix D and the number of negative eigenvalues of this matrix D. So this is a place where eigenvalues come into play, and they're not eigenvalues of the adjacency matrix. They're eigenvalues of this distance matrix. And so where n plus of D is the number of positive eigenvalues, of D, and n minus of D is the number of D. So before I give you the proof of the result, let me show you how this implies this thing about that we did earlier about the complete graph. So earlier so for the complete graph Kn, what is the distance multigraph of Kn? It's the same as the graph Kn. So that implies that the distance matrix of Kn is the same as the adjacency matrix of Kn, which is Jn minus In. Now for here, what is the number of positive and what is the number of negative eigenvalues? 1 and n minus 1, because this is minus 1 with large multiplicity. So therefore, the maximum of them is n minus 1. And then you plug in into there, you get greater or equal to n minus 1, you're done. Because that's the bound that we did with a linear system of equations. But this is more general because this one you can apply it for any graph you want. Any graph, you just go to the distance and it will get you a lower bound. So let me give you the proof of this result. So let's say so assume n of gamma is m, okay? Because n of gamma is m, we have this addressing, and what it means, we have this, so we have a decomposition of this distance multigraph of gamma into m of these biclics. Some of you ask, okay, what's so special? What happens now with these biclics? But I'll show you in a second right now. x1, y1, xm, ym. Okay, so we have decomposition. So again, this is a key thing. Decomposition partition, it will come back to some equality between a matrix and a sum of matrices. Okay, now here, this d of gamma, the matrix that corresponds to it is the distance matrix. Okay, now if you have a biclic, how does the adjacent a biclic looks something like this? You have some vertices here, you have some vertices here, you take all the edges here. In the graph, you could have edges inside here, doesn't matter, but you don't take them in your biclic, and you could have edges inside here as well. This is your xj, and this is your yj. Okay? So this is how the picture looks from the perspective of the graphs. From the perspective of matrices, how does the adjacency matrix of this graph look like? Now, without loss of generality, let's assume the xj come first, then the yj comes second, and then I'll give you a formula in a second. So this will look like the adjacency matrix of this biclic between xj and yj will look something like this. A big block of 0, and then here you'll have all one matrix. This is, let's say, xj. Say I have vertices here. Then this is yj, and this is the rest. Then here, so you have like 3 blocks like this, 0, 0, j, 0. Here you have the j, but is a transpose of this one. You have 0. And then what else? You will have 0, 0, 0, something like this. Because you don't take any of these edges. You take the vertices, but you don't take the edges, okay? Now, what rank does this matrix have? 2. So, and how can I write it in terms of the characteristic vectors of this subset xj and yj? So the characteristic vector, we talked about them when we talked about vector partition and interlacing. Let me call uxj the characteristic vector. So maybe uj so that it's easier. Uj is a characteristic vector of xj, and vj the characteristic vector of yj. And these ones, for me, all the vectors are columns. So these are n rows 1, okay? So this matrix is rank 2. How can I write it in terms of the characteristic vectors of uj and vj? So think about it like if I have if I take my uj like this, let's say I have, let me see, I'll put it, yeah, I'll put it here. So this is uj. So I have 1, 1, 1, where xj is, and I have 0 everywhere else. Okay. And then if I have, yes, and then if I have here 0, 0, 0, this is yj 1, and then 0, 0, 0. So if I multiply this column vector with this row vector, what do I get from this? Do I get this matrix, or I get some parts of it? I get this, I catch this block and 0 everything else. Okay. So the adjacency matrix of this will be uj multiplied by vj transpose plus vj multiplied by uj transpose. This is a rank 1 matrix, like we'll catch just this part and 0 everywhere, and this is the other rank 1 matrix, which is here, and it will catch everything else. Okay, so you can do that. So now the fact that I have a decomposition means I can write like a matrix equation between the distance matrix and these vectors, and these vectors. So let me see where I can, let me erase here, so I'll write it here. Decomposition into xm, this means that d will equal summation from j equals 1 to m uj vj transpose plus vj uj transpose. Okay. So now from here, I could get an easy bound for m, lower bound for m, just applying rank to everything. So I can say rank of d equals the rank of the sum, and the rank of the sum is going to be less than or equal than the sum of the ranks. And for each of these terms, I will get a 2. So if I apply rank, just by using rank, I get that rank of d is less than or equal than 2m. So I get m greater or equal to rank of d over 2. But as you see, for complete graphs, that's not good enough. That will give me n over 2. And the plus and minus stuff is better. So you have to do some trickery here to get a better bound than rank of because what is rank of d in terms of m plus and n minus? Eh? The sum of them. And I'm saying I don't want their average. My lower bound is gonna be the bigger of them. So this is a better bound than that. So we have to do a bit of work. Okay. So that's the equation. And now how do we interpret it? Okay, so let's consider the following subspace. So consider, let's call it U, which is the span of these vectors U1, blah, 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 UM. But I'll take the orthogonal complement of it. Okay, we'll see in a second why. Okay, so this is a subspace in a big space Rn. And let's see what's so special about this space. What's the reason why I picked something here? So, well, let me call it W for now. So take a vector W in W. Okay. Then what happens? W will be perpendicular on each of these U1, U2, UM. Then W transpose UJ will equal UJ transpose W will equal 0. for j from 1 to m. Okay. So now let's see what can we say about W transpose dW. So I will replace d by this, and so this will be a summation from j equals 1 to m of W transpose uj vj transpose w plus W transpose vj uj transpose w. So now when w meets a uj, it vanishes. So this part here is here, and it's going to be a 0. And when uj transpose meets a w, it also vanishes. So this part here, it's here, and it's also 0. So this guarantees that yours, this sum will be 0. Okay. All right. So w in here means this happens, that w transpose dw is 0. So why is that important? Well, that implies that w is not an element in the what I call E plus, which is the vector space, the subspace spanned by all eigenvectors corresponding to positive eigenvalues of D. So this is the subspace spanned by eigenvectors corresponding to positive eigenvalues of D. And it also implies the same thing by W does not belong to E minus, which is so here we have to think a little bit, but here's the, I can put here again to save my thing, exercise number 79, no? 28? No. 28? Okay, something. 29. Okay, thank you. So why is this happening? So if you are in E plus, you will be a linear combination of eigenvector of positive eigenvalues, and you take an orthonormal basis and so on. So you take a linear combination of those eigenvectors. When you go into to calculate W transpose dW, remember the calculations we did for the Rayleigh quotients. What came out there? You get with some kind of coefficients, squares, multiplied by eigenvalues. It's a summation of that form. Now, because you take a vector that is non-zero here, some of your coefficients, at least one coefficient is going to be non-zero. So the square of it will be positive. And because your linear combination corresponding to positive eigenvalues, all the eigenvalues that are in that linear combination will be positive. So when you calculate, essentially what I'm saying is that if you take W in E plus and W is not the zero vector, this implies that W transpose dW has to be positive. That's exercise 30, which is the same as exercise 29. So that's basically how you solve exercise 29. Okay. And the same thing here for all negative things. For the negative things, you will be strictly less than 0. Okay, the same problem. So now, how do you wrap this up? The way you wrap it up, you say, okay, so in this space, in Rn, I have W here, and I will have E plus here, and they intersect, this is 0. So other than that, they don't have any intersection, okay? And so what you'll get is that the dimension of W, so because W intersect E plus is just a zero vector, which comes from there, we get that the dimension that n is greater or equal than the dimension of W plus dimension of E plus. Now, what is the dimension of W? So W is this thing. So here is a span of m vectors. So inside I have dimension at most m or less. So if you take the perp, you get that dimension of W is greater or equal than n minus m. And you know that you'll have equality if and only if those u1, um are linearly independent. So then here you will get at least n minus m plus, what's the dimension of this E plus? N plus. N plus. N greater or equal than n minus m plus blah, blah, blah. You move the m to the other side. So you get m is greater or equal than n plus. And that's exactly what we need. And you can do it the same thing for n minus. Okay.
So for any tree, then operation again.
For any tree, what? I think n minus n plus will be 1 and n minus 1 will be n minus 1. I think, yeah. So, yes. So, in their paper, in their paper, Graham and Pollack showed also for any tree, n of gamma equals n minus 1. And for trees, I think n plus is 1 and n minus 1 is n minus 1. And then you have to figure out for trees how you do the addressing. But the trees have this very recursive structure. You have the leaf and so on, so you can do like you can address it in various ways. But in general, like I said, this parameter, if you come up with a graph, the lucky situation, which is like complete graph, for example, is a lucky situation where the construction you have gives you the same bound as this eigenvalue, and then you can say this is my number. But there are many cases in which this doesn't happen. So in many cases, you have a lower bound from here, and it's very difficult to increase the lower bound. So let me give you some examples. Can I erase here? Is it okay? Okay. Okay. Some examples. So for example, for a Peterson graph, if you want to address it, if you get you have to calculate. We did in the adjacency matrix, we calculated 3, 1, minus 2, 1, 5, and 4. You have to calculate the adjacency matrix of this D. Okay, so exercise 30, calculate it. And what you get from there is that the number of positive and negative eigenvalues, this greater or equal than max of n plus and n minus, I think you get a 5. But this was studied in a paper by Gregory van der Meulen, and there's one more author whose name escapes me, which is called an addressing of Peterson graph, and they could find a construction with 6. But then what they did in this paper, which I'm not going to put you through today, is they analyzed the equality case in this theorem, and they showed that equality cannot happen. If you have equality they concluded that the biclicks that you use have to be very large, and then they exceeded the number of edges that you had in the graph. So you could do from here, you could push it, they pushed it by one more, so you can do that relatively easy just by going through this analysis. And then, so, and even for Peterson to get this number is a bit of work, but this is 6. Okay. We have some paper, a paper with an undergraduate student and some co-authors in which we did other graphs. We calculated this parameter for other graphs, something called Hamming graphs. So Hamming graph H, let's say N2, we saw it already. We saw H32 earlier. The Hamming graph is you have n vertices in each row, and then you have n rows and you have n columns, and everything, everything in the same row and the same column is adjacent. So, but each of these rows is not a path, it's a complete graph, and each of these columns is not a path, it's a complete graph. So for these graphs, we can prove, we can address them, and we can address more general graphs. You can prove that this addressing for H and 2 is something like 2 times n minus 1. Yeah, so you need that that many symbols for this. So this is an n square graph. So the Winkler thing is at most n square minus 1, but you can do it with this. This is optimal. This is the exact value. Okay. Now, if you want to play around with this problem, we did a follow-up paper of follow-up work. So, and this is maybe useful because I think we have some code in the, like if you're interested in doing computations and so on, we have some code in that paper. This is a paper, I forget the year, but it's in experimental mathematics. So it's something called addressing Johnson graphs, odd cycles, and random graphs. And this is a paper with Alon, myself, undergraduate student at the time, Brandon Gilbert, Jacques Hulen, and Brendan Mackay. So in this paper, we look at a variety of graphs, including these graphs, which are Johnson graphs. So what is a Johnson graph? So Johnson graph J and let's say D. The vertices are all the D subsets of a set with n elements. So 1, 2, 3 up to n. We can write them like this, n, D. I write this as n between square brackets. This is the notation. Yeah. And the edges, you have some set S is adjacent to some set T if and only if S and T intersection is D minus 1. You just take one element out from one and you put something else in it. Okay. So for example, Johnson graph J and 1. I know it's late afternoon, you had your ice cream and so on, so you're half asleep. But let me wake you up with a question. Johnson and 1. The elements are one subsets of a set with n elements. Two of them are adjacent if and only if they're disjoint. So Kn. Very good. Okay. Johnson and 2. He has a different name. It's the complement of the Kneise graph, but it's something in terms of the complete graph Kn. The vertices are all the two subsets. It's the line graph of K. So in particular, Johnson 5,2, this is the complement of the Peterson graph. So in this paper, so Brendan Gilbert, he came up with an algorithm to address these Johnson graphs, and we could prove something that the addressing is at most d times n minus d. Now, bear in mind that these Johnson graphs, the number of vertices is n choose d. So that's very large compared to. And for the longest time, we thought, I mean, his addressing is fairly complicated. We give the algorithm is done in the paper, and you can check it out. And we proved that it's correct, it works. But then we thought, okay, this works, but there is example of NJ63 where this actually, Brendan Mackay did a computation and it found out that it's 8. This thing would tell us upper bound 9, but it's not. So this is not sharp, but it's still open, like what is this value? The other thing that appears in this paper that may be of interest for you is that, you know, like Winkler proved that n of gamma is at most n minus 1. And later on, there was in one of the papers of Ron Graham, he mentioned something that you would be tempted to conjecture that most graphs of gamma, this parameter is n minus 1. Well, we actually proved that that's not the case. So in this paper, we proved that for almost all graphs on n vertices, this parameter n of gamma is at most n minus something 2 plus little of 1 log of n. So this started as a first, that's why it's important for you to master both theoretical things and computational things. So with Brendan, I asked him, okay, let's calculate for graphs. You can get graphs to 10 vertices and so on, 9, 10 from using this naughty program written by Brendan Mackay. And he ran his algorithm to them, and we saw the numbers. So when you look at the numbers, it didn't look like these ones were most of the graphs. There were actually fewer. So then I talk about this with Noga alone, and he gave this example using random graphs that for most of the graphs, this value is at most this much. And the best lower bound here is something like n over 2, like in terms of eigenvalues and so on. So it's not known what this value will be for most graphs. So this is I think it's a difficult question. Yeah, let me tell you now which one is the hardest graph to actually, for which to find this addressing. And it's actually a very, it's a very easy graph to describe, but it's difficult to, nobody knows. So this is an open problem. And this is, you can find there is a paper by Alan Hoffman in 2001. It's called On a Problem of Zaks. And Zak studied a related problem in geometry. I'm not going to send you there. But what Alan Hoffman looked at is this graph. You have, we met this graph before. You take a complete graph and you just remove a perfect matching. Okay. So this is a cocktail party graph with 8 vertices. The cocktail party, well, you know, or you can say, yeah. So you have four couples, and nobody wants to talk with their significant other. So that's why you have a perfect matching there. And so this for this graph in general, for this cocktail party graph, let's say of 2m vertices, there is a construction that gives you something like 3m over 2, and this is depends on 3m over 2 plus something, depending if m is even or m is odd. There is some construction, which I believe it should be optimal, some recursive construction, you can get at most 3m over 2. Here, lower bound, by using this eigenvalue bound that I showed you with n plus and n minus, this was m plus 1. This is what Sachs did, I think, in the 1980s. That was the best lower bound. So 3m over 2 plus something m plus 1. And then Hoffman, in this paper, I think it's 2001, he added something like something, but it still doesn't reach here. So this is the best improvement of the lower bound for a graph that I know of, because Hoffman managed to prove that here you can increase the lower bound by not just one, by more, and then it still wasn't enough to get the value of this graph. So yeah, so simple graphs you cannot find this this thing. So okay, let me see. What do I want to show you? All right, so I'll stop here. I have about 15 minutes for the first part, or how much? It's 15 minutes. So I'll change the topics again to something else. So if you have any questions about this addressing, let me know. If not, we'll move on. I'll erase this. Okay. Okay. So okay. So let me tell you something about. So I don't know if I'll finish it now. I'll finish it. I'll definitely finish it in the second part. So let me give you an example of a recent application of eigenvalues for a different problem, which was for which the solution was given in a tweet. So the solution of the proof of this result was summarized not by the author, by somebody else, was summarized in a tweet. Now we're going to do the longer version of a tweet over an hour or something to tell you about this. So this is about what is called sensitivity conjecture. So sensitivity conjecture is a conjecture in computer science. If you look online, you'll find many descriptions of it. In computer science, people study these Boolean functions and so on. So functions that depend on many variables, and they want to see how the function changes if you change one of the variables and so on. Or that's called sensitivity of the function. or they want to see how the function changes when you change blocks of variables. That's called block sensitivity. And there was some relations from the 80s between these sensitivity measures, and then there was some conjecture about the inequality holding on the other side, and that has been open for many years. And people have tried to they've actually reinterpreted the conjecture in terms of a graph theory question. And the question in terms of graph theory is the following. So let's say for n greater or equal to 1, Qn denotes the n-dimensional cube. So what is this? We talked about it before. The vertices are binary words over 0, 1 of length n, and the edges you have x1 blah blah xn. So let me write it like this: x1 xn adjacent to y1 yn, if and only if there exists exactly one j from 1 to n where xj is not equal to yj. So the two words differ in exactly one position. So that's the cube. So, let's say start from n equals 1. This is 0, 1. And then, again, you can construct it like this. If you want a recursive construction, you can take the cube here. We talked about this earlier. You make 2 copies. Here, 2 copies of this. And you put a 0 to the end of one, and you put a 1 to the end of the other, and you join them by a perfect match. And then you continue. So you can do something like this here. So you have here 1, 0, 1, 1, 0, 1, 0, 0, and you can take another copy here. 1, 1, 1, 0, 0, 1, 0, 0. You add a perfect matching here, and then you put a 0 to the end here. You put a 0 to the end here. One. Thank you. One. Now you can do this. So the Hamming graphs that I mentioned a bit earlier, if I take, instead of the alphabet to be 0, 1 to be an arbitrary alphabet with more than 2 elements, that's going to be called the Hamming graph. So this is the cube is a special case of a Hamming graph. Okay, and the cube, you know that it's a bipartite graph. What are the bipartition, the color classes? Even and odd weights. So the ones that have even number of ones you put on one side, the ones that have, so the Qn, you have here 2n minus 1, you have here 2n minus 1. These are even and these are odd. Okay. So this problem about, the sensitivity conjecture is the following. Let gamma be an induced subgraph of Qn with more than half of vertices, 2n minus 1 plus 1 vertices. So this is just so that you don't just take, if you have 2n minus 1, you could just take this part, okay? Then the maximum degree of gamma is greater or equal than square root of n. So what this says is, if you take more than half of the vertices in the graph, you're guaranteed that among those vertices, one of them will be adjacent to at least square root of n of the others. I mean, for small values, maybe that's not going to impress you that much, because here, what does it say? If n equals 2, if I take 3 vertices, if I take the subgraph induced by it, the maximum degree of it will be at least square root of 2, but it's integer, so it will be at least 2. So if I take 3 vertices, no matter how I take them, I will take a path three vertices, so I will have a vertex of degree 2. Okay, so here it starts to get a little. If I take any 5 vertices here, A choose 5, A choose 3, A choose 3. 8 times 7, 56. Okay. Any subgraph with 5 vertices, the minimum degree will be at least square root of 3. So if it's at least square root of 3, at least, because you want an integer. 3. 2. Square root of 3? How much? Oh yeah, it's 1.7. Yeah, I was getting ahead of myself. I'm not going to draw this one, but yeah. Okay, so this is what Huang proved. Hao Huang. I forget which summary was, but look up online and you can see the paper on arXiv when he posted. And this was like a big news because pretty much everybody could follow the proof, understand what he was doing, and everybody was mesmerized that nobody has seen this before. Of course, you look at it, well, hindsight is 2020. When you see some, and then many people try to do the same thing for other graphs. Okay, so I'll give you the idea of the proof. So you have Qn, the graph here, and you take a subgraph here. Let's call it gamma. Okay. Now, the thing about graphs we had in one of the earlier exercises. What is the lower bound for maximum degree in terms of spectral things? Here, like in this statement, there's nothing about spectrum, nothing about eigenvalues. But we know before that maximum degree beats every eigenvalue, so it beats the largest eigenvalue. So it beats lambda 1 of gamma. Okay. Now you could try to do this, but the problem is that the eigenvalues of the cube, which we haven't discussed, but I'll talk about them maybe in a little bit. So let's do something aside here. Eigenvalues of Qn. Okay. N equals 1. This is Q1. 1 minus 1. N equals 2. Here's a quick trick that you can use to get from one eigenvalue to the other. Because you have this procedure of taking copies and doing this, you get the eigenvalues from before. If you had here lambda, then you're going to get lambda plus minus 1. Because you can take the same eigenvector from here, put it here. You can put it here, so it's going to give you lambda plus 1. Or you can take the same eigenvector from here, put it here, put the negative of it here, and it's going to give you lambda minus 1. So 1 minus 1, 2, 0, minus 1, 0, minus 2. I'll show you tomorrow a different way, but you can calculate this in a different way using characters. Okay. N equals 3. It's going to be 3, 1. You're going to have 1 with multiplicity 3, minus 1 multiplicity 3, 3 multiplicity 1. And it goes like this. Okay. So the problem is if you try to do here any, because this is induced, if you try to do some Cauchy interlacing about the largest eigenvalue, the bound that you will get for lambda 1 here is not going to be good enough for you to get square root of n. Okay. So what Huang did, used a signed adjacency matrix. So he took the adjacency matrix of the Q, and from it, he came up with another adjacency matrix. Let me call it Bn, which is symmetric, and he has eigenvalues, has entries 0, 1, and minus 1. So he just here in this adjacency matrix, you just have zeros and ones. So he just changed some entries he did it recursively, but you can do it in other ways. So he showed that for the cube with n dimensions, you can find a signing, so you can change some of the one entries to minus ones, such that these matrix values here will be square root of n with multiplicity 2 to the n minus 1, and this one will be minus square root of n with multiplicity 2 to the n minus 1. Which is kind of like, okay, there's a square root of n, so maybe there's something. Here, for the usual adjacency matrix, the eigenvalues of the cube will be something like this: n with multiplicity 1, n minus 2 with multiplicity, I think, n choose 1, n minus 4 with multiplicity n choose 2. So they go like this, okay? So they're minus n with multiplicity 1 and so on. So they go like this. But here, he showed there is a way. So how did he do it? He did it, so the idea was to think about it, this recursive thing about Qn. What you have is you have Qn minus 1, you have Qn minus 1. So when I'm looking at the usual adjacency matrix of Qn, you can think of it as what? It's kind of like a block matrix. I have here adjacency matrix of Qn minus 1. I have here adjacency matrix of, no, the other way around. I have here adjacency matrix of Qn minus 1. I have here adjacency matrix of Qn minus 1. And what do I have here in these blocks? Identity. Identity for 2n minus 1, identity of 2n minus 1. Okay? Now what he did the same thing. He used this to create this sign adjacency matrix. So he started, okay, B1 is the one for the first cube. It's identity I2. Nothing fancy there. Okay? Now B2, so in general, let's give you Bn. You look at this picture here, you will do almost the same thing. You do Bn minus 1 here. You put the same thing I2n minus 1, I2n minus 1, and then here you put minus Bn minus 1. And then you can, if you want, you can do induction. I think that's what he did, that if Bn minus 1 has eigenvalue square root of n minus 1 with these multiplicities, then Bn will have these eigenvalues. Okay? So how much time am I finished? Is it 3:30? Did I finish? I forgot.
2 more minutes.
2 more minutes. Okay. All right. So I'll leave it here for now. Obviously, exercise number 30 something, 31, is to figure out that the eigenvalues of Bn are this. Obviously, the easy way is to go find his paper and see how he. But you could, if I told you now how to do it, you can do it yourself. Just square the matrix Bn and see what happens. Because again, if you think about it, Bn having these two eigenvalues is going to be end up equivalent with Bn squared equals I to the 2n. And if you assume that this is the case for Bn minus 1, see what happens if you square Bn and multiply these things around. Okay? So you can do that. Okay, so let's take a break now.
Maybe you have to take 0, 1, 1, 0.
Yeah. You're right. Yeah. You're correct. B1, it's the adjacency. Yeah, it's the usual adjacency matrix of. Very good. It's the usual adjacency matrix of Q1. You're correct. Yeah. 0, 1, 0. Thank you. Yeah. Okay, because that's 1 minus 1. Okay. Okay. We'll take a break now. Okay. Welcome back, everyone. So let's just finish the proof of the sensitivity conjecture or theorem now. So before I told you about this, so this sign adjacency matrix for the n-dimensional hypercube is defined recursively as this. For the one-dimensional one, it's not the identity 0, 1, 1, 0. And then if you have such matrix for bn minus 1, you can make one for bn just by putting a block here, minus bn minus 1 here, and identity. And the exercise, basically, if bn minus 1 squared equals n minus 1 identity of the appropriate order, you can square bn, and you can get n times the identity. Okay, and from there, you can calculate the eigenvalues are square root of n and minus square root of n, and they have to have the same multiplicity. Okay. All right. So now this was, I think, so in the first step was so if there is a signed adjacency matrix, let's call it Bn of the cube Qn, such that Bn squared is n times I to n, or Bn has eigenvalue square root of n and minus square root of n. Okay. Now the second step in this proof was which was Cauchy interlacing. I mean, you can do it with bare hands without using this interlacing, but it's the easiest thing for me to tell you about is with Cauchy interlacing, and is as follows. So I will apply, remember, like the Cauchy interlacing theorem was true for any real and symmetric matrix. In most of the cases for us, we applied it for adjacency matrix, but I can apply it for a sign adjacency matrix. So this sign adjacency matrix is like a adjacency matrix, but some of the ones have been changed to minus ones, such that the matrix is symmetric. Okay, so you have here gamma, your graph. So you have so the graph Qn has 2 to the n vertices, and the graph gamma has 2 to the n minus 1 plus 1 vertices. So if you apply here Cauchy interlacing, what you will get is, so for this Qn, we'll apply it for the matrix Bn. So the matrix Bn will have square root of n eigenvalue with multiplicity 2 to the n minus 1, and you will have here minus square root of n with multiplicity with the same multiplicity 2 to the n minus 1. Okay. So if you apply here, you will get that the largest eigenvalue of gamma, because it has these many vertices, is going to be greater or equal. Remember that we had this in our eigenvalue inequalities. We had something that mu I, I forget, it was like mu I, is less than or equal than theta I, is greater or equal than theta I plus n minus n. Remember this part. Now we will use this part here, and you put, you see, you will put I will be 1, and here this will be lambda. You do the calculation, this n will be 2 to the n, this m will be 2 to the n minus 1 plus 1, and with the I, so this will become actually lambda 2 to the n minus 1 of Bn. Okay, this quantity here, so I is 1, this n for us is 2 to the n, and m is 2 to the n minus 1 plus 1. So when you do that calculation, you'll get exactly lambda 2 to the n minus 1. So the 2 to the n minus 1 largest eigenvalue. But that one is exactly like this one hits it right on the brink, because this will be square root of it. Okay? Yes. So what you do, you take, so very good question. So what you have this matrix Bn for the cube Qn, and let's say gamma is here a bit more than a half. You just take the principal submatrix of that. So this one is also plus minus 1, 0. So here it's Cauchy interlacing, but Cauchy interlacing for the usual adjacency matrix doesn't give you anything useful. But this matrix, because the spectrum has compressed to square root of n and minus square root of n, this matrix magically works. Yeah, so this is a, so for gamma you will have the sum matrix corresponding to the principal sum matrix of Bn, and for that sum matrix, this is not of the adjacency matrix. Let me be more precise. It will be lambda 1 of, let's say, AS of gamma. It will be like a sign adjacency matrix of gamma. Very good. That's a very good point. Okay. And then, so that's step 2 in this Cauchy interlacing. And then, question?
That's the submatrix of Bn, right?
Yes. So you just keep the vertices and the rows and columns corresponding to gamma. And because the numbers work exactly, that you get here 2n minus 1. Cauchy interlacing gives you that lambda 1 of this sign adjacency matrix of gamma is greater or equal than square root of n. And the third step is that we proved, where I asked you to prove that the maximum degree of a graph is always greater or equal than lambda 1 of the adjacency matrix. You can prove that it's also greater or equal to largest eigenvalue of any sign adjacency matrix by the same type of argument. I think we did the proof. And if you use that proof, it works for any sign adjacency matrix of gamma. So there is a sign adjacency matrix like this. That's where kind of the magic happens. Cauchy interlacing, the largest eigenvalue of that sign adjacency matrix is at least square root of n. This is known. Maximum degree always beats largest eigenvalue. So maximum degree will be at least square root of n. Okay. So that's this proof. And again, before he obtained square root of n, the best bound that people had was log of n. And this square root of n, people proved before that this would be best possible. So there are some subsets that you can pick that this works for, obviously for n a perfect square. Okay. So that's that. So what I'll do for the remaining time now, I will tell you the equivalence between this notion of sign adjacency matrix and the notion of a two-cover of a graph, because that will come into play tomorrow when I'll tell you a little bit about expander graphs and so on. So for now, I'll talk a little bit more about this notion of sign adjacency matrix and how it relates to something else. So sign so I can put here like an equivalent. It's like they're going to be equivalent to something called two covers. Okay. In the following sense, here we'll have matrices. Here, two covers will be graphs. But I'll explain what I mean by this. Okay. First, let me give you a definition of a two-lift or a two-cover of a graph. So. And I'll do the general definition. I'll do an example. So let me give you here you have gamma graph. From it, we can construct the following. Gamma prime will be a two cover. So for maybe I'll do it this way. So gamma. You'll see in a second while I'll do this picture. Gamma prime. This will be the following graph. You have as vertex set of the graph, Cartesian product with 0, 1. So from each vertex from here, I will make two copies of the vertex in the two covers. So I have here, let me say this is my graph. Let's say A, B, C. This is a complete graph. And here I will make in gamma prime, so my gamma is K3. In gamma prime, I will make two copies. I'll make an A0 and an A1 copy. Okay. For B, I will do the same. I'll have a B0 and B1, and for C, I'll make another copy, C0 and C1. Into it here, B0, A0. Okay, so I want to define what is the double cover, and this will be some edge set. So the vertex set, it doubles. So every vertex here gets 2 copies up here. Okay. Now what do you do for every edge? For every edge, when you look at these two, so A has 2 copies here, A0, A1. B has 2 copies, B0, B1. You have 2 choices. You can either add a perfect matching like this, or you can add the other perfect match. There are two perfect matches between the parts. So here I chose to do this. Here I chose to do this. And here I choose to go do this kind of diagonal. Okay. So the vertex set is this, and then the edges, if you have, so how I do it here, if X is adjacent to Y, that means that here you have 2 possibilities. Either X0 is adjacent to Y0, X0 is adjacent to Y0, and X1 is adjacent to Y1, or you have X0 adjacent to Y1 and X1 adjacent to Y0. So that's the rule. So you won't have, there isn't just one to cover. There will be, for each edge, you have 2 choices. You either keep the edges parallel or you make a cross. Make sense? So this is called a 2 cover. Now, why is it called a 2 cover? I kind of draw them like this so that I show you why is it a cover. So what happens is there is a function f from the vertex set of this 2 cover to the vertex set of the graph itself. And this function will take f of x0 will equal f of x1 will equal x. So basically these two vertices, I map them into a0, a1, I map into a, b0, b1, I map it to b. So it's kind of like they're covering in that sense. And what is this function? So this function is f is a graph homomorphism, which is something that I haven't defined. But graph homomorphism, what it means that it maps edges to edges. In our graph, like if I have so A1 is adjacent to B1, where does A1 go to? Goes to A, B1 goes to B. There's also an edge here. I mean, here everything is an edge, so it's relatively easy. But a graph homomorphism maps edges to edges. You have to make a distinction between graph homomorphism and graph isomorphism. In graph isomorphism, you map edges to edges and you map non-edges to non-edges. So that's kind of the difference. Okay, 1. So this is 1. And second, for every vertex in the cover, for every xj, if you take this function f and you restrict it to xj, to the vertex xj, and to its neighborhood, union gamma xj, this function is a graph. It's going to be locally a graph isomorphism. So, for example, if I take the function and I pick a0 and I look at a0, let me see. So, what do I want to say here? Yeah, it's well, it's not a graph isomorphism. This will give you a biject between this set and the image of it. Yeah, it doesn't have to be isomorphism. Okay. For this example, let's just okay. This is the I have this example. Now, can you recognize my drawing is a little bit messy there, but can you recognize what is a graph on the top? Cycle C6. So cycle C6 is a two cover of so C6 is a two cover of K3. Obviously, if I have two copies of K3, 2K3 is a two cover of K3. That's also true because you don't, all the edges are parallel. Something for you to try at home. The cube Q3 is a two cover of K4. So try to see how the cube is a two cover of this cube is a two cover of K4. Okay.
Sorry.
Yes.
Explain the second.
So for the second one is kind of locally that, so what happens is locally you'll have a bijection. So you'll have, if I have pick a vertex A1, it has neighbors B1 and C0, there will be a bijective to A, B, C. Okay, so that's what it is. Okay. All right. Now, here's the relation between, if I have a two cover, let me show you how this relates to a sign adjacency matrix of the graph. That's yes.
Small question.
Yeah.
So either you take these two conditions or you take these two conditions, right?
Yeah. But for two cover, this is what I will work with, because this gives me like a concrete way of defining. So basically, I have a choice. So for each edge, you pick some kind of you make some choice if you're going to keep the edges parallel or you're going to cross it. So let's say you have that.
Here in this picture, A0 is connected to C1. Yes.
Yeah. Yes, A0 is so this edge AC, you decided not to keep the edges parallel, you decided to cross them. Yes. So A0 is connected to C1, A1 is connected to C0. So this gamma prime is one two cover of this graph. And because you do this procedure, it can happen for every edge. Here you have three edges, you will have 8 possible two covers. I mean, so they will be isomorphic to each other because you will get sometimes to either 2K3 or you get C6. But two cover is not unique. There are many. And if you think about it, sign adjacency matrices also, they're not unique. So this is where the connection is going to be, because for each edge, I choose to have these parallel edges or to have them cross. It will be something similar now for the sign adjacency matrix. I choose to either make the entry in that position to change the ones to minus ones. That's going to be the gain. So if I have a two cover gamma prime, I'm going to make a sign adjacency matrix AS as follows. So AS will be V by V, but now AX in the position XY will be the following. So I will put a 0 if XY are not adjacent, so those don't interest me. So I have to deal with what happens if XY are adjacent. So if X is adjacent to Y, and in gamma prime, X0 is adjacent to Y0, and X1 is adjacent to Y1, I put a 1. So if I have parallel edges, I just keep a 1. Okay? And you can imagine what happens if X is adjacent to Y and x0 is adjacent to y1, and x1 is adjacent to y0. Then I put a -1. And then otherwise, if there's no edge in xy, so otherwise if x is not adjacent to y, there's no reason to put anything. Okay, so let's do an example here for this. So for K3, for this adjacency matrix of K3, let me label them A, B, C, A, B, C, and you know what it is, 0, 0, 0, 1, 1, 1, 1, 1. Okay, this is the adjacency matrix. Now, the sign adjacency matrix for that picture. So so let me draw that, maybe that picture again here. So this is A0, this is B0, this is C0, this is A1, this is B1, this is C1. Okay? So now, if I look at, so that's a picture of the graph. Now, I want to write here, I will write here the adjacency matrix of gamma prime. Okay, this is going to be a bit big, but I will do it the following. I will do here, I won't write it A, comma 0, I'll just put A0, B0, C0, A1, B1, C1, A0, B0, C0, A1, B1, C1. Okay. So, this is the adjacency matrix of the big graph. I'll write it down in a second. But before I do that, what I want to show you here is that the two cover that I have here, what is the sign adjacency matrix that I define? AS of this graph gamma, AS of gamma. It will have the same labeling as A, B, C, A, B, C. I have 0 here. Now, I look at A and B. For A and B, the edges were parallel, so I keep a 1. For B and C, the edges are parallel, so I keep a 1. And for A and C, I decided to cross, so I put a -1. So that's what I mean that this sign adjacency matrix, it's just obtained from this matrix. You pick some entries and you change them to -1, but you have to change them. So you have to change them so it stays symmetric on both sides. People have studied also like something where it's called skew symmetric, in which you change the one only on one side of the diagonal. Okay, but here this matrix stays symmetric because you change the one, like we changed this 1 to -1 on both sides. Okay, but obviously you have -1, so there's no non-negativity or anything. Okay, so what I want to convince you now is that for these two cover, you can recover the adjacent, if you look at this bigger matrix, so the graph, the size of your graph just doubled. And what I claim is that you can get the eigenvalues of here from this matrix by taking the eigenvalues of the original graph and the eigenvalues of the sign adjacency matrix graph. That's what will always happen. So that's why I say that sign adjacency matrices are equivalent to two covers, because if you give me a two cover, this is my sign adjacency matrix. If you give me a sign adjacency matrix, I can represent it by a two cover. Make sense? Yeah. Yes, with respect to these two cover. Yeah. So what I'll try to show you now is why the spectrum of the adjacency matrix of this graph will equal the spectrum of this union the spectrum of this. So this is one way you can do it, so this is not written in many parts as far as I can tell you, but you can already, you have enough, we talked enough about equitable partitions that you can kind of sense there is a connection. So if I have this graph here, the partition into these blobs, does it look like an equitable partition to you? Well, inside these blobs, I put nothing, so it's zero regular. And what do I see between every blobs? I either see a perfect matching, in this case, there are perfect matchings everywhere, but in other situations, you may not see anything because if there was not an edge in the graph, there wouldn't be an edge here. But either way, it would be an equitable partition. What will be the quotient matrix of this partition? In this case, it will be the complete graph, will be the adjacency matrix. So in general, the quotient matrix of this partition will be the adjacency matrix of the graph. And that tells you by using this equitable partition that this big graph, which is twice the size, inherits the eigenvalues of the original graph. And sometimes these eigenvalues of the graph gamma, they're called the old eigenvalues because the two cover will get the okay. But the two cover has twice as many vertices. So you have to have some new eigenvalues, which is the stuff that we talked about with the equitable partition. And you can use this argument, the argument there, to say, okay, how are these, so the eigenvalues from here that appear here will have eigenvectors that are constant on these parts. You just take an eigenvector for gamma and you just copy the entry here, copy the entry here, and so on, double. The other eigenvectors, how are they going to be? They're going to be perpendicular on these parts. So if you're perpendicular, you're going to be, you know, one is the negative of the other. And then that leads to the sign adjacency matrix. Here, let me give you a slightly different proof by this example. So let me write you down this adjacency matrix. Okay, I'm sorry, I'll put you through a lot more pain. So 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 0, 1, 0, 1, 0, 0, and here will be the same 0, 0, 1. Okay, so in general, what will happen when you do this signing of the adjacency matrix, let me erase. What is it? Question? Which one? Where is it? Here? First row. A0 and C1. No. This is A of gamma prime. This is the original adjacency matrix. So I want to show you another way of looking at this adjacency matrix of this big graph. You can get the spectrum from these two. So I'll just want to show you a different way, okay, by this example. So what will happen in general that so gamma is my original graph and gamma prime is the two cover, is the bigger graph. So the adjacency matrix of gamma prime will be something like this. You will have here, if you put the vertices of gamma times 0, it will be some matrix A1, here will be some matrix A2, it's a matrix, it will be here some matrix A2, and here, what do you notice? A1, it's the same thing here. It's the same matrix here. So in general, that's what will happen. And what do you notice about this A1 and A2? Okay, so if I put, so here, this is A1, this is A2, how much is A1 plus A2? A of gamma And how much is A1 minus A2? Yes. So based on this, you can do the thing that I mentioned earlier, as follows. If you have A, so let me erase here. If I have A gamma U equals something like, let's say, some lambda times U, then I will do this thing about constant on the parts of the partition. So this implies that A of gamma prime times U will equal theta. This is exactly what I said about equitable partition. If I have an eigenvalue lambda here with U, I just put the values of U in all the parts of So if I had in the graph in A, if I had U1, I put U1 here. So okay, so that's one part. And then if I have a sign adjacency matrix times of V equals, let's say, theta times V, this is for a different eigenvalue for the sign adjacency matrix. Then I can do A gamma prime V minus V. These are going to be the vectors which are perpendicular on the parts, and this will give me also here this. Thank you. This is lambda, and this will be theta V minus V. This requires proof, so you have to prove this. This requires some kind of proof, and you can use this. Yeah. So you can use this to prove this fact. You see, like if I have A gamma prime and I'm multiplying it by a vector UU, because the matrix is in this block form, what do I get? I get A1 plus A2U, A2 plus A1U. But what is A1 plus A2? It would be AU, or AU of gamma. So this is going to be lambda U. And the other one, if I have this other one, if I have A gamma prime times V minus V, this will be what? In my matrix, I have A1, A2 meets. So it'll be A1 minus A2 times V. And this other one will be A2 minus A1 V. But what is this? This will be ASV minus ASV. So this will give you theta. So you're lucky you just escaped one more exercise, but that's the proof. Okay. And then this will be because if you take a basis of eigenvectors here, then all the UU will be linearly independent. So you'll get half of the eigenvectors. If you take a basis of eigenvectors here, this will be linearly independent, and these ones and these ones will be orthogonal on each other. So you have the whole basis of eigenvectors. So that's the spectrum. Yeah. Sometimes you can have repeats. It does. It may happen, but my point is that from here, so from A, you will get n eigenvectors, and they will become these eigenvectors UU for the two cover graph. Okay. These ones were a basis. These ones are linearly independent, so you're fine. So you got half of the spectrum. Then you go here. You don't care if theta is the same as lambda. You just play this game again. ASV is this. Then V minus V will be an eigenvector here. All the V, if you start here with the basis of eigenvectors for AS, all the V minus V's will be linearly independent. And anything from here will be linearly independent from anything from here because they're orthogonal. So this you have a basis of eigenvectors. So that's your spectrum, obviously including multiplicities, because you could have repeats in the lambda, you could have repeats in the thetas, you could have repeats between the two parts. So again, this is important to know because again, it's a different perspective, and you can say, well, what's a big deal? Well, this is a big deal because you have a question about matrices, is a question about graphs, and I'll show you tomorrow an application in the theory of expanders, which is very important, where people have used this connection to prove some big results. Now, for the result of Huang, he looked at this part. I have no doubt that he knew about two covers and so on, but it turns out that his construction of this sign adjacency matrix is equivalent to a two cover of the cube. And it turns out that that was studied in the 80s by people in finite geometry who wanted to, they wanted to look for two covers of n-dimensional cubes that do not contain C4. So you see, in the cube, you have many C4s. They're everywhere and so on. So people were looking at how can I lift the cube such that the n-dimensional cube such that it doesn't have any C4. And it turns out the cover that was in a paper in the mid 80s, it's the same sign adjacency matrix that, so after he proved this, people observed, well, by the way, this was here, but in this situation, people were looking at the finite geometry problem. They didn't consider, I don't know, they didn't know, they didn't look at this problem. So the moral of the story, it's important for you to look at different angles at the problem because you never know what may be useful. Okay, so I'll stop here for now. Okay, thank you. Yeah, of course you can be disconnected because you make everything